Okay, awesome. So, guys, welcome to this banner exploitation workshop. We'll start with buffer overflows, and we're going to explain what buffer overflows are, um, and and then try to actually perform some buffer overflows on some vulnerable program. In between, the goal of this workshop is to understand it from first principles. So ideally, we want to leave nothing that we don't understand. So we need to understand every different step and deeply, get a feeling of, okay, like we really know what's happening here instead of just running something, and magically getting a root cell and be like, okay, somehow it worked. That's what we don't want. So we want to um, lift the veil of confusion um, that surrounds memory exploitation. Now, I'm DSP. I'm a security researcher. I am one of the founding members of 2f30.org, which we still are, like a community of Unix uh, aficionados, let's say, and like software appreciators. And sometimes we write software too. And the past years I've been involved in security research and vulnerability research. So what are we going to try to do today? First of all, we're going to mention the famous Art of War from Sun Tzu, where he actually talked about buffer overflows or not. I guess this is the internet, so you need to choose what you believe these days. But he might have said that, what I'm mentioning here in the slide. But what we will actually try to do, apart from this cheesy trolling that I'm trying to do here, we will try to understand first how an executable is running in memory and how it's laid out. Okay, so when we load an executable, what's happening? Like, where are the different parts of the executable loaded in memory? That's important because the first thing um, in war, right? It's like knowing where you are and having an understanding of your surroundings. So you need to know where everything is in memory, so that you know if something is possible or not. First of all right? Then we will start writing some assembly. Okay, we will write assembly. I know it might sound intimidating, right? And you're like, what? I've never written assembly. Well, I'm here to show you that it's not hard to write assembly. It's actually easier than most programming languages to write simple things in assembly, right? To write complex things in assembly, you will need to uh, develop a structured character. So you develop a procedure, but to write simple things in assembly, it's actually pretty easy. Then we'll learn what system calls are and how to interact with the kernel. Then we're going to examine a running program and how the memory looks like, and we're going to see there um, where the program keeps space for our data and where the program is keeping space for its own control flow data. And we will see that when we manage to mix these two things and get our data on top of the control flow data, or we manage to um, somehow change the control flow data, we can change the flow of execution of the program. So we can send the program wherever we want. Okay. And then at the end, we're also going to learn something called POM tools, which is like the modern CTF way to interact with programs and perform all this memory exploitation stuff. So that you can actually gain some experience and see how you would play in a normal CTF, not just having doing everything by hand, which is what we do before. Deploy for a program that I have for you here, and exploit it and read the flag or gain a root cell or whatever you want to do. Okay, so I'll pause for a second, see if there are any questions on the large scale plan here that we have. Seem to be doing good. Now, again, ask questions. I'm sometimes monitoring the chat. So what we're trying to do here, I just hope to explain that to you, is considered a dark art. Okay, because we take beautiful programs that trust us, that that just want to do their thing, and we are very bad to them. We change them, we make them do our own thing. We change their full character into becoming puppets of what they were before, and now they do our own bidding. So it is indeed a dark art, and it is a skill that you should only try to employ if you're sure that you're going to use it for ethical reasons. That's something to always remember when you deal with security. You want to learn all that stuff and use it for ethical reasons, and people are going to pay you a lot of money to not keep your ethical standards up to to the level that you should. But try to avoid that, and remember that you should only be doing this sort of job if you are going to actually be a positive impact in humanity, and that doesn't mean usually helping someone gain a lot of money or helping a state actor be more aggressive. Okay, so I'm hoping that I established that right now. So as we learn about these things, we're going to go down to low level, right, and learn how the low level stuff works. And in a sense, I have emulated this whole workshop. It's like as if we're going down to Dante's Inferno, right? We're going to lower and lower level every time, and we're breaking the understanding that we had before of how a program works into we're seeing that there was just a veil, and now we're learning more of how it actually works inside. And the more you learn how it works, the more scary it becomes, right? Because the more you can manipulate. So let's talk about executables. Executables, if you've noticed in Linux, right, you might run a program in Linux, right? And if you remember, there's that command called file that's going to try to understand what type of file something is, and it's going to tell you. So right now, for example, on your computer, if you're on a Unix system, you can run file and then give it an executable like file space /bin/ls to see what bin ls is as an executable and what file is going to tell you about it. It's going to probably tell you that it is an ELF file. ELF means executable linkable format. Okay, and it is a way that the operating system packs a program in a way that it can actually execute it afterwards sanely. We're going to learn about these commands that we can inspect the program, disassemble it or see where the sections of it are. Maybe you have already seen all these things, but yeah. The commands that we're going to use in this section is obj-down, read-lf. Okay. Now, we're talking here about compiled programs. You write a program in C, you compile it, and then you should be able to just run it. Okay. But you think about it, when you compile a program, it becomes like a sequence of assembly instructions of bytes. That means something to the CPU. You might think, okay, why doesn't it just become like the exact so that I'm imagining, and why don't I jump straight into it so that I actually just execute the program? Okay, that would be a valid question, right? I mean, what is this whole ELF thing that we have, and why does it need different sections and all that stuff, right? Now, the L in ELF stands for linkable, and you might know that sometimes we just compile the source to an object file, compilation into an object file, and then we link object files together. And so that, for example, we don't, when one program uses printf, right, or one program uses what else, like my brain's freezing, something from liben, something from the power function or the exponent function. And we don't always pack this function in the executable, but we have it in a shared library. Okay, and all these programs are using shared libraries together in a nice, and well engineered way. Okay, so to do that, to be able for the programs to use external libraries or become libraries themselves and all that stuff, that's why you can imagine that's one of the needs of why we need to have different sections where in the programs we define, for example, what is read-only data only for that, or what is the text segment of the program where it has a code, or what is the data segment, and what is the initialized variable segment, the uninitialized variable segment, and all that stuff, right? So there are different sections that kind of do a lot of bookkeeping, and the linker, when it links programs together, it knows how to efficiently link programs together and where to place them in memory. This is a very hand wavy right now. All those things I just said, they're very hand wavy, but they're just there to explain the need of ELFs. Okay, so I don't know. Did anyone try to run file on binls? I'll try to run file on binls right here. So hope you can see like my terminal here clearly. I'll run file /bin/ls. Okay, the first thing it says ELF 64-bit LSB. Okay, least significant byte pi. Of course, happy birthday, Nicholas, for today, right? There is pi for you, but this pi means position independent executable. Okay, this is what pi means here, and it means an executable that the positions are that the linker can relink it in a way that nothing points back to an exact position before, but the linker can reposition it in a way that all the positions are relative to the segment it is, so that this is what the position dependent executable means. And this is an essential thing to have, like, modern protections in executables, like address space layout randomization and other stuff, or have executables being easily linked. It's important to be able to have them to be position independent. Okay, and it says it's x86-64, the architecture of this CPU that I'm running. It's dynamically linked. Okay, and there is an interpreter, and that interpreter is the loader, the Linux loader, lib64 ld linux, blah, 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 blah. Now I'm just skimming through these things. That doesn't mean I completely understand them or they're not extremely deep. All these things that I've mentioned about now can take a lot of reading to actually gain and feel, understanding of them. So don't worry if you're like, it's the first time that you see these things, because these are not easy things, right? And you shouldn't be expected to know all these things, right? Maybe some, right? So don't worry about it. Like, we're going to learn the important, and the relevant things. So I did file, and I'm mentioning here objdump. Okay, I'm mentioning objdump, blah, blah, blah. Section headers, I'm giving some parameters here. Section headers, symbols, and disassembly. Okay, so the first task I'm asking you to do here, it's like disassemble files / returns main function with objdump. Okay, now let's run first of all objdump on binls, right? What we said, we have a binary here. We have binls. Everyone has this ls binary in their systems. So let's run it. Objdump -n intel, I said here, and then I said binls. I'll just run like that. Now, I'm not giving any other option, so this will fail. It will say, okay, what do you want to do? With this, I will say, okay, I want you to give me section headers. I think this should be the correct command. Section headers. And wait, is it just headers? Section, sorry. Okay. So it's giving me a couple of responses back here. Let's buy it to less. Okay, it says bin-ls, it is this executable, and it has certain sections. Okay, so a binary has different sections that as it runs, it can execute. Now, these are too many sections, and honestly, I don't know half of them. Like what they do. But I can tell you some of that I know. Okay, so for example, I know that the dot init section here relates to things that would run before main starts. Like if you remember, like when we run a C program and it has a main function, which supposedly the first, the entry point of the program. Well, it's not really the entry point of the program. Init function is the entry point for the program usually. With Linux and libc how they are, and then init would relate to things stored there before main. Now we also have the .text segment, which is confusingly named text, I understand, but text actually holds the data, the instructions of the program. So .text always holds the actual code of the program. Okay, so the instructions of the program that are compiled into machine instructions, they are stored over here. And the raw data, you can imagine, it's read-only data. Okay, this has another section here in the executable. Okay, and the BSS, it's the global, uninitialized data. Okay, that are here. By the way, if I make any mistakes, please jump in and correct me, or just give me a break, because this is like sometimes all these things are not useful for me. So if I say something wrong, please excuse me. I'm not an expert in all these things. In data here, this has, as you can imagine, actual data of the program. So let's look at these sections and notice that they have different sizes. First of all, it says here size, and we see that init has a size of only of hex 17. That's pretty small. The text section code of this program has a size of hex 1591e. I don't know how much this is. Okay, and the read-only data has a 52d3, and blah blah. So we see every section has a size, and then it has like this VMA, which means virtual memory address. Okay, and these are like kind of the virtual offsets of memory that these things are going to be loaded into. Okay, now how exactly memory is laid out and how the kernel gives memory to user space programs and all that stuff, it is a bit out of scope, right, for this lecture, because we can be here for weeks still talking about all these things, right? But you can imagine that in the end, when a program runs, it thinks it has, the full memory, that it would be available to it, right? Every program on a 32-bit CPU thinks that it has 2 to the 32 bits of memory available to it. And on a 64-bit CPU, it thinks it has 2 to the 64 bits available to it, although, of course, it doesn't. Okay. But this is the goal of the memory manager, to give to a program the illusion that it has infinite memory. So the program doesn't have to deal actually with, allocating physical pages and all that stuff. It just goes and does its thing. Now, of course, if you have a computer with 8 gigabytes of memory, you don't have a swap, declared, and then you try to allocate 16 gigabytes of memory, it's going to crash. Okay, that's expected. There's no magic happening here, right? But the system is designed to give to the programs the illusion of infinite memory. Okay, and this idea, again, of breaking an executable into different sections is one of the important things of being able to, to lay them out in memory so that things are tidy. Like the read-only data is only in this section, right, where it has a size of 0x52d3, for example. It has this offset. So then maybe, for example, because it's read-only data, the kernel can make sure that none is going to write into these pages, for example, right? It might say, this is read-only data. If I see any writes in this page of data, I'm going to say, I'm going to stop the program, right? for example. So that's one of the benefits of breaking things into sections. And again, we also talked about dynamic linking. And see, quick questions on this. I'll proceed a bit. And I'm also going to mention that here I'm saying, please use this -m intel parameter. Why? Okay, I will explain a bit. Let's do, so we did section headers. Let's do the -t to see what this does. Okay, so -t, this program on binls, again, we're doing binls. It's going to say, oh, I don't have a symbol table. So every -t, is trying to see what's the symbol table. And what's the symbol table? The symbol table would be a table with all the variables in the program and where they are, so the debugger can actually do stuff with it. Like, it can tell you when you're in the debugger, you might say, I want to see what's the value of this symbol, and the symbol table would help with that. But because we're looking at binls and we haven't compiled our system with debug support right now because it would be 3 times larger, in terms of space. And that's why this program doesn't have a symbol table. But we are going to compile programs with symbol table, and we're going to be able to see that in a bit. And then let's do also the -T, which is the other the other option I told you, which is this disassembly. Okay, and let's do that. And wow, now this starts to get pretty interesting. We actually see the assembly code of the program, right? And of the different sections here. It says the disassembly of that section is blah, 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 this. The disassembly of that section is blah, blah, this. Well, let's try to search for the word main here. And I'll just go a bit down because I know that, interesting. I'm looking for init now. Anyway, I won't make a fool of myself, and I don't know why binls didn't find the main, but anyway, and it can show me the disassembly of the program. So what I'm asking you to do over here for this task is to disassemble files returns main with objdump. Okay, so let's go and do that. In your containers, VMs, whatever, you have a directory called files. I have it right here. Okay, files. So please go into files by doing cd files, and then you will see certain programs, and you will see a makefile, right? Using the makefile, we can build these programs, and I've written, already some targets for you. So I would like you to build a return program. So I would like you to type make return, and this is going to build it. You can do make return, and this is going to build this program using this command. Okay, and we'll talk a bit about this command in a bit. But once you build it and you have like this return binary here, and you can do file on it. It's going to tell you it's an ELF 64-bit, LSB executable statically linked this time. This is important. But once you do that, once you have return built as a binary, I would like to go ahead and examine it with objdump -d. So I would like you to disassemble return and go and look for the main function in that. I'm giving you 30 seconds to just do that as questions or whatever, and then I'll just jump in. Questions? And wants to say anything? Said objdump -m intel -D for disassembly and // return. That should work, and I'll path it to less. And I'm getting, the usual sections here, the disassembly, and I'm going to go to main. There it is. I went into main. I don't know if you can see it. It is this thing that I'm highlighting right now. Okay, and this is the assembly code, the disassembly code, right, for the main function of this program. Okay, and now see if I can break my screen here. And then I'll go on the side and find some directory. And I would like you to see this program now. So this is the C program that, oops, sorry, on the right side is the C program that I have written here. And on the left side is the disassembly of that same function, plus with, a lot of other things here. Again, I'm going to let you take a moment and look at these two things, okay? And then we'll talk about it. So I hope you have some familiarity with C. You will need it here entirely for anything related to operating systems still until Rust becomes a bigger thing. And then we have like this function called main, which, as we said, is the the entry point for this program, supposedly. Okay, it takes a number of arguments. This is showed here in the int argc. It says this is the number of arguments I'm providing to it, and this is the actual argument string array that I'm giving it to it. Anyway, like C is beyond scope here, but what we want to see here is that what this program does is it just returns 42, which is the answer to everything. And it can return 42 because it returns an int, this function. So int return 42 checks out, right? And so I would like you to see over here and tell me if you can spot this on the assembly. I see someone. And Nicholas, is your audio up or it's Nicholas audio? We lost him. He said my audio is not working there. Can anyone else hear me? Anyone else can hear me or not? Maybe it's my audio. Okay. So your microphone is not working. Okay. Awesome. Okay. Well, I don't know if you can fix or something, but then again, I'm monitoring the chat. So let's do it from the chat. Can anyone spot the correlation between return 42 and this piece of assembly program over here, on the left side? And you should be doing this in your own computer right now. I mean, if someone doesn't do this, on your own VM, then let me know why you can do the same thing as I just did here. But again, take your time. I mean, ideally, I would like someone to find what is the connection between these two, right? So there's one thing that's very special, very unique. This 42. Can you spot 42 over here? Would you show the command you used again? Yes. So the command that I used over on the left side here is what am I doing? Yes. The command I use is objdump -m intel -D for disassemble, and then I'm disassembling the the files return binary, which I built by And then I pipe this to less, to actually read the whole thing. But you can pipe it to a file, and then you can open it with VI. I don't know whatever you want to do, like how you're going to read it. But because if I don't pipe it to less, it's going to be like going to just keep going, right? I'm like, I don't have time to read this, so I need to pipe it to a pager, right? To less, for example, or more, and then I can search in there by pressing slash, which will allow me down here. If you see this change to slash, so I can search, and then I can say main, and this will allow me to. I'm pressing N to go to the next match. This is how let's use. Go to main here and see this assembly. But for example, since you mentioned it, I'm going to do it some other way. I'm going to redirect this on tmp, return.thisas, for example. I'm creating a new file, and then I'm going to open it with vi, right? Tmp return.thisas, and then I'm here, with vi, and I can do like again main, and bam, I'm here on line 897, right? Which VI is polite enough to tell you. Okay, for example, right? That's one way to deal with it. You can I forgot to set up the workshop, right? Okay, the Docker build isn't working. Yeah. Yes, the Docker build requires you to be in the specific directory. Okay, so it requires you to be in the directory that contains this Docker file. So yes, as Nicholas saying, do the git pull first. Okay, and yes. Okay, some people are trying to set up the environment again here, and I will kind of go back here in these slides. Okay, and remind you that right now we're doing the objdump command, which dumps either information about an executable. We're using the dash m intel parameter so that we see the assembly in. There are two formats that you can read assembly that programs have traditionally. There is the Intel format, and there is the AT&T format. They are equivalent, but AT&T has things split, or Intel has things split depending on which school you subscribe. But we will be using the Intel syntax for assembly here. So, for example, I'll give an example. When you want to move to a register, the value 7, in Intel syntax, you would say move to the register the value 7. So the destination comes first, right? As, for example, the same thing happens with memspy, right? When you do memspy, the destination buffer comes first, right? Or so this idea also transforms the assembly too. While in AT&T syntax, it's flipped, right? So it's important to make sure we're all using the same syntax, because otherwise we'll be reading things opposite, inverted. Of course, soon you realize that this does make sense, right? But yeah, we'll be using Intel syntax for these things. And now we're using the dash D for disassembly, this as here, and we're disassembling the files returned binary. Awesome. I see you guys are progressing there. And yeah, so anyone wants to jump in and tell us if this 42 here, if you have spotted it? Guys, again, this is an interactive workshop. It should be, right? And hopefully the people that will see this recording, they will be as confused as you, and maybe you by speaking and by saying like what you don't understand, you're going to help them out. This is not a lecture. Like if you want a lecture for buffer, find it on YouTube, right? This is an interactive thing. So jump in and let us know if you can spot, or if you can't. Can you see where this 42 appears in this disassembly over here? Fantastic. Okay. Okay. One person has seen it. So 0x2a is actually decimal 42. Okay, but it's written in hex, and it's polite enough to actually say 0x in front of it, right? Okay. So now let's imagine what's happening here. We see that this value, this 42 value, we see it's involved in a move instruction. Okay, so and involving the register EAX. Okay, and as I told you before, because the destination comes first in Intel assembly, this instruction move EAX 0x2a gives to the register EAX and the value 42, okay, or 0x2a. It's exactly something like just in the hex representation. Now, we will, as we said in this tutorial, we are going to write assembly. Okay, so it's important we understand, start understanding some assembly slowly, right? So move is one of these instructions that we'll use. So we better, get familiar with it. Okay, we can move to a register a value. Okay, now what is a register? You might ask. Some of you, I'm sure, like you haven't used registers, directly. Okay. A computer comes in with, a modern CPU comes in with memory for your programs, right? And there is like the memory, the RAM, as we know, that you add, next to the CPU, right? It has a channel to communicate with the CPU. Then you have the cache. Usually, you might have heard, the L3 cache, the L2 cache, the L1 cache, right? There are different levels of cache, which is memory that is in the CPU. So these are like memory cells in the die of the CPU, right, or very close to it, which allow the CPU to store some memory for things that it's using often. And L1 is faster than L3. That's why it's called layer 1 cache. It's the fastest cache you can get. So it's like things that are being used very, very often and very frequently. They are always staying there so that the CPU can access them very fast. Okay. And then we also have the registers, which are ultra fast. The registers are like tiny, like pieces of memory, and they have each one has their name, and that's what the CPU uses to actually perform instructions, right? For example, there is always a register called the stack pointer that shows where the stack, and we talk about what the stack is. The stack is just the beginning of space that people can store things, is in memory, right? Or we have another address for what the return address of something is, right? We have like these registers that are tiny pieces of memory in the CPU that the program uses to actually, to actually operate. Okay, and because we're talking about x86 64 now, like AMD64 and assembly, we have registers that look like RBX or RAX or RBP or EBP and all stuff. Now, I'll just talk about it for, again, this is, the difference between ER and AX and the first letter here can tell you how much of a register you want to use. When you use the R, it's the full register. And because we're in a 64-bit machine, so when you're using the R in the beginning, you're using the 64 bits of that memory. When you're using E, you're using just the 32 bits of that memory. When you're using nothing of the two, just AX, for example, here, you would use the 16 bits of that memory. And when you use AL, L stands for the low bit, the low byte of that, you use only 1 byte of that register. Okay, so these prefixes allow you to specify how much memory you want to use. And if you start noticing now things here, like this guy said, move EAX, the value 49. Well, according to what I told you right now, some very observant person here might be like, okay, why didn't he just use move AL 0x40, 0x28 or 49, 42, sorry. Because in 1 byte, I can go from 0 to 255, right? I have space to use just AL. Why did he use EAX here? That would be a fantastic question to start thinking about. Or why didn't he use RAX, which is the full register, the full 64 bits here? The answer to that has to do because I asked it to do so, because I said I want you to return this as an integer, and an integer is traditionally 32 bits in this architecture, so 4 bytes. So that's why he did 4 bytes here, right? He did exactly what I told him to. But if I asked this function to return, long, right, or uint for whatever, this would be RAX here. This is a bit of a diversion here. What do we do after we are done downloading the VM? The VM or the container? I'll jump back here in a second. You guys are debugging. So can I get like a check from the people who have managed to just disassemble this and see the thing with stamp? How many people have managed to do that? So I get a feeling who did it. Hassan's raising his hand. I guess that means he did it. Anyone else? I know Panda has done it, and then I know Nicholas has done it. Nicholas, did you manage to run the command, the obsdam command? And track, is your VM or your Docker, did it compile? Are you okay, or are you still like? Because we can take a moment to stop here and wait for you. Fantastic, awesome, good news. Okay. I'm waiting for your guys' answers here. And as I'm waiting, I'm going to show you how the assembly looks like when we don't say Intel, right? Let's see some AT&T syntax. And we'll see the same thing with AT&T syntax now. Just to going back to main. And here we are. Now with AT&T syntax, if you notice, look what I just told you. This value, this thing is now flipped. You see the move EAX 0x to A. Now it has this syntax that takes the dollar in the beginning and says move 0 $0 to A to EAX. So this is a syntax we don't want to use. If we start seeing stuff like this and all the stuff, we know we are using AT&T syntax, so we need to ask it to stop and give us back the nice Intel syntax, and like this. And we're going to show you the thing, how it should look like. Again, this is the syntax we like. This type of thingy and brackets instead of parentheses. And show the register to reference. We love Intel, of course. Yes, we love Intel. Okay. So yes, I agree. Intel is way easier to read, and actually, it's from the people who made the CPU. So we better, use the manufacturer's language in that case. And as much as I love Bell Labs and AT&T, this for assembly, Intel is better. Now, again, return 42. Again, we said we know how it looks like in assembly. Now, I want to talk a bit, and this is where we're going to focus, right? Next, on the things around this. We have this thing, push RBP, move RBP, RSP, blah, blah, blah. What is he even talking about, right? I have no idea what all this stuff is. And what is red, not all the stuff, like it's confusing, right? But we're going to try to understand it. Now, before we do that, though, I would like you to also notice over here, like, on this instruction, now we kind of got this, right? I mean, we can wrap our heads around how to give the value 42 to a register. Okay, to the register EAX, right? Here, you will see these are the actual bytes of the instruction. Okay, that means that when the CPU sees a byte B8, hex B8, followed by 0x2A, followed by 000 bytes, and when the CPU sees that, it's like, I know what he wants me to do. He wants me to move the value 2A, 0x2A, to the register EAX. And now look, this value here 2A is encoded as an instruction. Like, I mean, you know, this is pretty obvious, right? But maybe it's not, right? So the value 0x2A comes right after B8, and evidently B8 means put something to the EAX register, right? And B8 has to mean EAX. It can mean RAX. There has to be another byte for RAX, right? Because just these two guys over here mean put the value 2A to the EAX register. Okay, so now we see that these are the bytes that the CPU is reading and knows what to do. Okay, and for example, C3 means red. Okay, and blah blah. You see also that there are different size, right? This push only takes 1 byte to be encoded, but this move takes 3 bytes to be encoded, and this move takes 5 bytes to be encoded. This is what we call a variable length architecture. Okay, so this is not necessarily a thing that happens in all CPUs, but this CPU can encode instructions with different lengths. So instructions that are seen often only take 1 byte, while instructions that are more rare can take 6 bytes. And that way it can save space, can run faster. Okay, because it needs to read less bytes. Okay, to do that. If it always had to read, 16 bytes for every instruction, that would be pretty simple, to write a parser for. But it would be slow because you'd have so many wasted bytes that the CPU needs to read every time. Okay. So yeah, Hassan, good luck. The assembler decides this register. Let us see. Who decides where to store? You mean who decides to put that in EAX, right? That's the question. And why doesn't he put it in EBX? Okay, that's a fantastic question. And we see that there are certain registers that are important and that are not up to the assembler to control, but there are other registers that they have some play there, and they can choose. The compiler can choose where to put. Where to put everything. In this case, we learn that the AX, the AX, EAX, or RAX register always holds the return value of a function. So that is why it's necessary, because we're returning this to the parent, the caller, to whoever called us. It's necessary that we put this in the AX register so that they know to read from. This is a convention, and we're going to talk about this convention in a bit. Okay, but that's a great question, right? In this case, where it's important to know what is a return from a function, and it's specified by this convention, says we put it in AX, RAX, or EAX. Okay. Fantastic. I think we're doing good here. Let's continue. So we have some idea. I mean, we saw our first assembly. Okay. Now, I talked about the sections and where they're mapped, right? Okay, let's look at the sections for this binary too. Okay, let's do the dash, instead of doing dash D now, we'll do dash section headers. Okay, for this binary. And so I'm going to stop here. I'm going to do like ops down dash. Sorry for that. And that's dash section headers. And we see, like, again, certain sections here. Okay. And then I would like to let me see which program will run forever now. Let me try to think of a program. We can do anyway. As you see the sections here, the operating system is also capable of giving us the things where something has mapped its sections, right? And there is the /proc file system. So for every process, you can do, for example, a cat/proc self. That means, you know, the actual process that is invoking this. So this would be the process of my shell here, maps. Okay, and if I do this, cat self proc maps, I'm going to see um, for this binary that's running, okay, and actually I was wrong, cat proc self maps will execute on the context of cat, the command cat, okay, and it's going to show me where the sections of cat are mapped. Okay, so it's going to say, for example, that the stack of cat was mapped from this address to that address. Okay, and it's mapped as read and write. The let me see, the heap of cat, if cat wants to do, you know, like a malloc and put stuff on the heap, it's mapped from this address to that address. Again, read write. Okay, and so on and so forth. Okay, so the operating system also, and this is actually, you know, here you can also see the code of cat. And for example, you see that this segment is mapped as Rx, so read and executable only. So we can expect that in this area we'll find, like, you know, the instructions of cat. As cat, you know, is a program that can next file. Okay, so again, two ways to kind of inspect this. This is a static way while the program is not running, where it shows kind of only the offsets. And this is where, while the program is running, it's where the operating system actually placed it, but the offsets should be the same, if that makes sense. So if you see something being at an offset of 18 here, you expect to find at an offset of 18 here as well, only, you know, with a different starting location. Okay. And again, don't worry too much about it, but it's another way of inspecting where sections are loaded, proc self maps or proc PID maps. And let's see, questions. What was your command to compile the return C program? Okay, so to compile the return C program, I went into files where I have all the programs, okay, and I have this return.c program. And I also have a make file for you. A make file is just a recipe that says to compile the return target, you run this command. So I only need to run make return. Make is a command that reads the make file, reads the target that I want for it to compile, and by doing make return, it's going to compile the program. If it says return is up to date, it means the program is already in there. So I either need to do rm return, look, not return.c, I'm not removing the source, I'm moving the binary. Okay, and then I'm rerunning make return, and it's recompiling it. Okay, the program, and then I can do stuff. Does that help? Make return, yes. Okay, that will compile the return program. Okay, and make clean would clean all the binaries, and also like, yeah. Yes, you need to make sure you're in the files directory. Yes, good catch. Yeah, okay, I will proceed a bit. So now, I said before that every ELF has an entry point, and kind of think that this entry point is main, right? Because that's where we think, you know, execution starts. But we have this command called readelf. That's another command that we can use, and let's run it on the return binary. So when we run read elf -h on the return binary, it gives us back a lot of stuff. First of all, it says the ELF header has this magic number. Now, for all of you that have taken the digital forensics course, you know we've talked about like magic numbers. Magic numbers are just, you know, a pre-agreed number that file formats put there so that other programs know what is the file format, right? It's it's a way to identify yourself, put yourself in a box so that other programs can know what you're all about, right? So there is a certain sequence of bytes that is the magic number for ELF files, and this has this magic number here, okay? Now the class says ELF64, blah, 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 blah. But if we look over here, we see entry point address. This is important, okay? And this is telling us in which address of this binary the execution starts, okay? So when we invoke this program, what is the first address of this program that it's going to be executed? And this guy is telling us it is 0x4016C0. Okay, let's go take a look, right? Again, this is 0x4016C0. It should be the same for you too. These addresses should be the same between all our systems. So I will again, decompile the program and, save it somewhere nice. And then I'm going to go and 4016C0. And I'm going, oops, sorry. Yeah, sorry, it's wrong. And 4016, and I'm going to do 4016C0. I can't find this address. Yeah, 4016C0. Okay, I found it. 4016C0. And it says this is the underscore start function, the entry point of this program. Okay, kind of hinted at it before. I said we think that main is the entry point of the program, but in the end, it's not really main. Usually, it's in this Linux API, interface, it is the underscore start function usually, right? Or underscore init sometimes, right? And this is the first thing that is executed when we start running our program. So the first command that's going to actually run when you start this program is going to XOR EBP with EBP. So this is going to zero out the EBP register. And just wanted to point that out. It's a useful exercise for you to also do that again by yourself. Let me see. Is the underscore start a default for certain compilers? Now, yeah, I think, the answer to that would be yes. This is on the edge of my understanding, right? I mean, I'm not sure who demands that, I don't know if someone asked for it to be called start. I don't know who enforces this interface. Is it the kernel? Is it POSIX? Is it I don't know. Okay, I don't really know who is requiring that, and if you could potentially just have some other function on start. I think honestly that if you go on the ELF and you say on the ELF header that the entry point is something else, it's going to be respected. Honestly, I don't think that the system would care that you're not, starting from a function called underscore start and blah blah. Plus, if you have a strip binary or whatever, you have removed all symbols. I think that it's not going to care. All it wants is in the ELF here to have an entry point of know where to start the execution of this program. But as you say, there are higher forces in this world, like reptilians, that they make all these. They're part of IEEE and all these committees, and they make our life hard. But we're not going to discuss more about this, right? So anyway, so okay, I hope you kind of did that and you kind of saw this thing again. I'm just showing you some tools and showing you how to kind of look into binaries, kind of with we're not doing anything specific here. I just want you to get kind of comfortable at looking and kind of getting a mental model of how this runs. Okay, and as we say here in the slide, eventually main will get called, right? And indeed, main will get called. You can follow that. We might actually be able to follow this assembly enough from start to be like follow it. Okay, so we're like, okay, here this guy is pretty polite. It tells us over here you're doing a call on this address 403C00 libc start main. Well, that's pretty obvious, right? I mean, call it's calling a function, right? Let's go there, 403C00. Okay, we're now here in libc start main. Okay, and this is doing other things here, blah, 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 something with the environment, something with the stack. I'm just looking at, all these names here because it can collide. But eventually I would expect that I would see something with main here. Eventually I would expect that somehow I'm going to be sent to main. There is this libc init first. Maybe I have to go there first, and then, maybe from there I'm going to go to main, right? That's possible, libc init first. Okay, and there's this init. That is a good, that's a good candidate. So let's go there. 401000, 401000. So we're now on init and blah, 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 and kind of hit that spot over here because it's calling something that puts on a register. So anyway, I know this is going to end up in main, but like you can't really see it right now because it has this funky dynamic value here that goes into array X and then calls the register directly. But I can guarantee to you that eventually we're going to hit main. Okay. So let's see questions. Okay. Let's proceed. We completed the first task. Fantastic. Okay. So now, before, if you remember, like as we were seeing, where 42 is stored, we kind of, I asked you, what is this push EBP up there, blah, blah, blah. How are functions called? Okay. And then I'm telling you that as we're learning things, we're going deeper, like, slowly in deeper and deeper levels of the Inferno here. So this is the first level. So welcome here. In this level, this painting by Stradanus, and he, on the first level of Dante's Inferno are supposedly the philosophers, and people who don't really believe, So here we are right now among these people. Socrates supposedly is here, by the way, and we're trying to make sense of what's happening. So we'll try to understand how functions call each other and how functions can return back to where they were before they called another function. Okay. Because if I was just able to call a function, then I was never able to return back where I was, then that's not a fantastic system. How can I chain, programs together like that? So what's going to happen is that we can have here the parent and the child, and they're not very good names. I should be using caller and callee. So please, wherever you see parent, think of caller, and where you see child, think of callee, right? But then the parent, first of all, because before he calls a child, he needs to save the spot where he wants execution to come back after the child is done. So it's as if you're sending your child off to do some work. Child labor is not a problem in this context. Okay, so you're like, please, kid, you go do that, and when you come back with what I requested you to do, we're going to continue, making this cake, for example, right? So this is where the execution is going to resume after the child comes back from whatever you asked it to execute. Okay. So then you also, this is the first thing, what we're talking about here, like where we save the execution. Then we kind of give the child some space to work with, right? Because the child needs to do stuff, right? It needs to bring the materials for the cake, right? So we need to give him working space. So we say, okay, you take all this area over here and do your stuff. And then when you're done, please have it clean. That doesn't mean like zeroed out, but like at least, when you're done, I'm using that area and you're out of the picture now. Okay. So that would be the second point. And then I'm setting the top of the stack. It's where I'm allowing the child to start working now. And I'm saying, okay, from here on, it's you, right? And do your thing. And when you come back, I might use this space. Okay, this is the high-level idea of what happens on a function prologue. Okay, let me see. Uh, yes, yes, there is a lot of tangents in Inferno reference in this talk. Okay, so let's see how it actually happens. This will involve, saving some registers and blah blah blah. And now I talked about registers before. Um, One register that is very relevant at any given point is what's called RIP. It's not rest in peace. It is the instruction pointer with the R prefix before. That means that we can use the full 64 bits of the instruction pointer. So the instruction pointer always points to the next instruction to be executed in a program. Okay, and in the end, this is the pointer that we need to gain control of, okay, to alter the execution of the program. So the first time you see it over here, it's a very important, what am I saying, pointer? Sorry, I mean the register. So for some reason, I meant the instruction register, not pointer. But what am I talking about? The instruction, the RIP register. Okay, so of course it's a pointer because it points the next instruction. Yeah, but it's a register. So so the parent is going to first save his idea of what the next instruction should be. Okay, it's going to be after you're done, we're going to continue with execution over here. That's the first thing he does. He saves it. And how does he save it? By pushing it into the stack. Okay, the stack, we said this is shared area where everyone, both us and the programs are working with, right? And that's what causes the problems. But it's going to push it on the stack. It's going to just add it onto the stack. The stack, you can imagine it's a thing that adds up, and then we pop and we reduce it back down. Like it's an idealized stack. By pushing something, we add to it. By popping, we remove from it. So call that instruction that we saw before, like call EAX that we saw before, it translates to push the instruction pointer. It's literally an alias, right? Call means push RIP. Wherever you see call a register, it means push the RIP, your current instruction pointer, and then go and make your RIP whatever is in that register. Okay, so change your execution afterwards to that. Now the parent, we say, pushes the instruction pointer, and the child pushes the RBP and moves the stack pointer to the base pointer, and then subtracts from the stack pointer whatever size of memory it needs. Now that's a lot of stuff over here. So let's decompose it a bit. I want you to imagine of these two registers, we know what RIP does, what IP does now. Okay, it's the next instruction. Now, what is RBP and RSP? I want you to first imagine that memory grows down. Okay. See, yeah. So memory grows down. Okay. The RSP, the RBP is on the top here, and RSP is on the bottom. Okay, over here. So then you put RBP over here and RSP, and they're in the same place. And then you push something into the stack, and RSP goes here. Then you push something else into the stack, RSP goes here. You push something else into the stack, RSP goes here. Then you pop something, RSP goes back up, RSP goes back up. Okay, until it's again the same place as RBP. So RBP and RSP are the two different ends of this stack that you're working with. Okay, and so when the child pushes the RBP, it saves kind of where the where the top of the stack was. Okay, then it moves the current bottom of the stack to his top of the stack, RSP to RBP, move RSP to RBP, and then make some space, new space on the stack, according to how many locals, how much memory it needs to work with. Okay, this is what the prologue of a function does, and we can see it visually here. We say, okay, before the child was called, that was the parent's base pointer. That was one maybe an integer that the parent had here, and another integer that the parent had here, and that the top of the parent stack was on address 16 over here, 0x10. And then after this prologue, what happened? First of all, the parent called, called the child, so that pushed the instruction pointer over here. So you see now where the top of the stack was, there was the saved instruction pointer here. Then the child pushed the RBP, so then the RBP is saved here in the stack. And the child moved his stack pointer to the base pointer. So the new child's base pointer is now this. This is the top of the stack for the child. And then the child starts, removing stuff from the stack, making space in the stack for their own variables. This is how a function calls another function in assembly. Okay. Again, I know it's not very obvious. Take a minute, ask me any questions here. Like, you want to go through again, like, we can internalize it. Take some time and internalize it. So let me know if it works for you. Yes, base pointer and stack pointer. Yes. Again, the base pointer points to the beginning, of the stack, like, the top of the stack, and the stack pointer is where the current top of the stack is, right? Okay, maybe I say the start of the stack and the top of, if we see this, start of the stack and the top of the stack, where you're adding and removing things. Okay. So now the epilogue here, which is the opposite. Now we need to undo all this action. But before we go to the epilogue, let's go back into the obs dump that we did before and just see it. Okay, I want to see it here in main. So I'm back in main, and let's see the steps that this function did. It indeed said push RBP. So main has been called by someone, right? By start. Okay, so main is the child now, right? So the first thing the child does is push the base pointer. Let's validate we have it correct. Here, push RBP. Okay. Then, Then move RSP on RBP. Yes. And then give us some space in RBP, in RSP. Now, in our case, main didn't didn't have any local variables in this very single function, so it didn't need any space. So the last step here that we say subtract from the stack pointer, your local variables. Well, main didn't have any local variables, so it didn't subtract any. Okay, so this it's important to be able to identify, these prologues and epilogues. Just looking at assembly, because even if I saw this at assembly, I know it's a function call, even if it didn't tell me that, oh, it's the beginning of a function. I know that there's a function call happening by this. Okay, so I need to go and see who made me land over here, and I started my function, right? Because it wasn't the previous guy, you see, it wasn't frame dummy that continued execution here. Someone had me jump over here, and I started executing. Start, okay, or libc start main or whatever. Okay. Questions? Okay. Okay, we are pretty, yes, I'll continue faster. So the epilogue is the opposite. Okay, the epilogue is a child and takes the RBP and moves it to RSP. This should be a comma here. And then pop is popping something from the stack. And then ret. Ret means, what does ret do? Ret is important. Ret, and let's follow through. It was here, the child base pointer, remember, like the local of the child and the other local of the child and the child stack pointer. And once the child starts calling that stuff, it's moving the base pointer and the stack pointer. So it's moving his base pointer on the current stack pointer. So now all this stack is gone, right? All the stack doesn't exist. The top of the stack is over here now. Okay, here. And then it's popping the base pointer. So it's taking that off the stack. And then we have this saved instruction pointer here. And ret pops that thing. Ret is actually an alias for pop to read. So it takes that thing and puts it on the instruction pointer. And that's how execution flows back into the previous function. And if you see what happens after the last pop, well, we're back to where we started. It's just the parent with two locals, and all the rest of the stack, has been cleared, right? It's not of use anymore. And the RSP is back here. Okay. Well, let's so was just before, how do we write assembly? Okay, and what is the importance of this register, RAX? Now, I kind of hinted that the return value of a function always goes into RAX. Okay, now, where do the arguments of a function go? When you have a function that has one argument, again, by convention, on Linux, on x64, the first argument of the function will go to the register RDI. The second argument of the function will go to the register RSI, RDX, RCX, R8, R9, blah, blah. Now, if a function has like 16 arguments, then after R9, I think, or maybe R10, it starts using the stack. So you push the extra arguments in the stack. Now, the task for this one is to write in assembly the previous program. Okay, and I want us now to return, instead of returning 42, I want us to return 0x1337. Okay, so for this, we're going to use files return.s. So guys, let's go open this SIA track. Okay, can you open this return.s file? Let's see. I'm opening it here, and you will see something like that. Okay, it says we're using Intel syntax. Let me see, you guys, if anyone, let me know. So we see this, and I've left with XXX and the things that you need to put in here. So remember, the goal for this is to call the function foo, and yeah, S means assembly. Yeah, capital S means assembly. And now it's the first time, like, I mean, you can actually, maybe for some of you, it's the first time that you're actually writing assembly. Okay, but this is, you will see, you have like this main and another function that we declared, like foo, and you see that main calls ret. Okay, so it will return, and I guess we can call foo from main, right? And let's try to write this together. Okay, so the goal is to write a function that returns 0x1337. And now here's the thing. Not only I'm going to make it a bit. Not only foo needs to return 0x337 to main, but I also want main to return 0x337 back to whatever the caller is of the operating system. Okay, so take like 20 seconds to think about it, and then let's work on it together. And I'm going to give you all the instructions that you might want to use, like all the names of the instructions you might want to use. You want to use call, and you want to use move. You don't need to use any other instruction, I think, to make this thing work. So call and move are the only two instructions that we'll be using. And going back to the reference here, let's see. The return value of something goes in RAX. And I'm having end takers here, end takers on who anyone thinks they have something. Main calls foo. Yes, main calls foo. So how do you do that? Just what would be the instruction to call foo? Just call foo. Okay. So here I'm just going to say call foo. Okay. Now I'm calling foo. Now foo needs to return 0x1337. How do I do that? I need to um, okay, we have here ret. Okay, so you're using ret here. Let's think about it. Ret is that ret doesn't take any arguments. Ret is just return. Yes, correct. We need to move to RAX, which is where we store our return value. So we said this is the calling convention. We're going to store the number of the return value to the RAX register. Okay, so we're going to move, correct, move. Let's do it all together. And here, we're going to say move to EAX or RAX. I'll do RAX. Okay, and 0x1337. This, and then I'm going to say ret return from this function. Okay, so that's my take on it. There might be other ways to do it. Okay, you might say here move EAX or move maybe AX. You can try and see what's going to happen. Okay, but let's try this. Okay, it's our first assembly, possibly, right? Let's make sure we understand it. We're going to say we have Intel syntax. We're talking about the section text, which remember text is the code of the program, right? We're going to declare two global symbols, main and foo. Foo is going to be these two instructions. So we're just putting 0x1337 on REX and returning. And main is calling foo and then returning. Okay, now I said that I would also like main to return 3037. So would it make also sense for me to say also this here? What do you think? So that main also returns 1337. What do you think? It would be unnecessary. Yes, it would be unnecessary because in between these guys, nothing changed the value of RAX, right? So I can just keep using RAX as this. And normally, RAX is going to still be set to 1337, hopefully, when main returns, right? So let's try it. I'm going to exit now this, and I'm going to compile my return program. And if you see on the make file, I have made a target for you called ret-asm. So I can do make ret-asm. And it should compile this assembly program. Okay. And you see now I'm not using GC, I'm using AS, the GNU assembler, saying that I want 64-bit with Intel syntax and blah, blah. It's going to make an object file, and then I'm going to link the object file, because in the end, I want to create an ELF executable again, otherwise I cannot run it. Okay, so I have this return-asm thing, and I just run it. Now, it didn't print anything, but how can I get the return value of something from the shell? Well, probably you don't know, but if I input dollar and question mark, okay, here, this dollar question mark is going to give me the return value of the status of the last program that texted. And it says 55. Okay. Now that's interesting. Okay. Why is it 55? First of all, and to kind of try to make sense out of this. Now, if I do and I say, okay, what is 0x37? It's a big number. Okay. It's 4,919. Okay. So maybe is it possible that 55 here, just that this interface doesn't expect, that maybe expects value from, from 1 to 255. Maybe it expects 1 byte. So I'll go back and change my program, okay? And I'll be like, okay, I'm not going to make it return this big number, but I will return 133 in decimal, like I'll do this, for example, like a smaller number. Okay, and then I'm going to recompile it. You have to rm first, rm the return ASM binary, and then make return ASM. And then when you run it again and check the return value by $? It's 55 again. Why? Why is it 55? Let me try to put it over here again. And I'm going to do the same things. I'm going to make a rm, make return ASM, run it. It still is 55. How about I make it something less? I'm like, okay, I'll make it 33 over here. I'll remove the binary, make it, run it. Oops, sorry, make run and check the return value. Okay, now it's 33. So there might be a reason that, very big numbers, for example, are not returned back to the operating system probably as, as expected directly. Because I saw that, I started with a big number, an RAX, which is a 64-bit number, but yet the operating system never gave me anything above 55 as this return value, okay? Which is interesting to see why this happens. No, I don't think it's any honest. I think it is. It has to do with the operating system only expecting 1 byte, and if there is a certain larger value, it just goes back to 55. And you see that 33 and the numbers below that are actually returned by the operating system. Okay, this is in a sense, I think, a historic limitation that we're seeing here, right? That back when Unix was created, didn't expect that the return value could be 8 bytes long, like a whole RAX, right? It probably only was 1 byte long, right? From 0 to 255, right? So I think that's what we're seeing here. But we saw that we can actually manipulate it, right? We saw that that we successfully returned something. And to make a point here, I don't need this. This is going to be persisted. So if I make like if I make RAX, like 12 here in foo, I don't need to reset main. It is redundant, what you said before. It is redundant. So I make write ASM again. I run it. And it is 12, right? You see? So it is what we expected in terms of flow, but it wasn't in terms of the number. That number was too big to be returned back to the operating system. But if this was like a normal function, that a function called another function, that would not be a problem. It would actually be able to consume the whole, RAX here. Okay, so the problem is this guy returns an RAX, but the operating system reads probably an AL, or some lower thing. Okay, lower part of the register. Now, let's proceed. Okay, fantastic. I mean, guys, first of all, congrats, because you persevered and you wrote your first assembly, and I hope from that you see like, okay, it's not very intimidating until now. Okay, we can work with this. Okay, let's proceed. Now, let's write a function that adds two numbers together and call it from main, okay, and have main return the result of the addition. Okay, now here's going to be a thing. Now we know we can't really put very big numbers. Seems that 55 is our top. So let's not try to add, 133 and 64, whatever. Let's try to add something simple, like 9 and 12, right? human numbers, numbers for people, not machines. Okay, so 9 and 12 it is, because these are very nice numbers. So let's try to make the same thing now. We're going to have this add.s function. Okay, and I'm giving you also one extra instruction that we need here, like the add instruction that adds register B to register A, adds register B to register A, keeping the result in register A. Okay, and let's do it. We totally have this. Okay, let's do add.s, and I've made it again here for you, like, it's pretty ready. Okay, so on add, we need to add these two numbers together. The question is like, add will take two arguments. Okay, the first number and the second number. Where do we store these arguments? Where do we store these arguments? On which register? One register is going to be 9, and the other is going to be 12, because these are the numbers that we chose. So who can set it up? Set it up for me. Let's do it. Yes, RDI and RSI. So RDI is going to be 9, and RSI is going to be 12. So let's make sure we write our move, move instructions properly. So once we write our move instructions, and you can get going, RDI, RSI, right? Okay, so we're here in main. We're like, we want to call add. Okay, but before we call add, let's fix the arguments. We're like, okay, move RDI 9. Move RSI 12. Okay, now I have the two arguments ready for add. Now I'm going to call add. Well, add is going to do the add. How does this work? Well, add RDI, RSI. So now RDI has the result of this addition, and I need to return it back to, my caller, right? How do I do that? Last, I want to see someone giving me the missing instruction here. What do I need to do? Because now my result is on RDI, but I need to move it to where for my caller to see it? I need to move it to RAX. Correctly, move RAX RDI. Fantastic. Okay, so we are moving before we return to RAX RDI, and then we're returning, and we should be good to go, right? I mean, this looks legit. Now, I'm saying here, make sure you return the result of add back, but we kind of hinted before, like, if I don't touch, RAX over here, I'm good to go, right? So it should be there. So let's see. 12 plus 9 is 67, right? So I'm doing the makefile, make add ASM. I'm compiling this program. I'm running it, add ASM. I'm checking the return value, 21. It's legit. It's correct. Okay. I mean, this is the first addition that you got with assembly. And like, I can sense the excitement from the other side of this. Okay. But it's I think if you manage to do that, it's pretty cool. I mean, it shows that, okay, this, you have some control over this. Fantastic. Are we good to continue? Let's go. Let me also turn on the lights because it's becoming darker and darker here, and like, I mean, we are going down the layers of hell, but, we should have some light with us. So let's continue. Okay, now we're kind of, okay, since we finished with assembly, I mean, like, we've totally got this. There are some things that I haven't mentioned, but I mean, you think I'm ironic, but I'm not actually ironic. I honestly mean, it's not that hard assembly, right? And it just, being tidy with what you write, and that will get you very far with assembly. Now, the question is like, how do we interact with the kernel? How do we actually make system calls? How do we make things happen on the computer? Okay. Well, again, it's a very similar calling convention, right? I mean, we have these system calls here that we name. One can do read, and I'm giving you the important ones for this course. There are many, 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 many more in Linux. Okay. Now, one is read, the other is write, the other is open, the other is close, and the other is exit. Okay, the ones that we're going to need. Now, you might have used them from C if you have written in C. Like, for example, exit with an error code, like it's number 60 in decimal, and it takes an error code, and whatever that error code is, comes back and says this program exited, with minus 33, for example, when that means out of money, whatever it is. Close takes a file descriptor and close, and it's number 3. Open takes a string, which is a file name, the flags that you might want to open it, like read only and write only, blah blah, and the mode, and opens a file and gives you back a file descriptor, which is kind of can be referenced as an integer. The file descriptor is, it's a big struct somewhere in the kernel that is indexed by that integer, but it means something. It means you can read and can write and keeps a position and all that stuff. Write, it takes a file descriptor, a buffer of data and how much you want to write from that buffer to that file descriptor and writes it, and read the same thing. Okay. Now, these instructions are how every program interacts with the kernel. So when you actually, type anything, when you do hello world, it's going to end up being a write instruction. Okay, a write system call in the end. Okay, so for now, again, as we see, the system calls also follow a calling convention. The registers still go the same place. Like the first argument is on RDI, the second argument is on RSI, and third argument on RDX, and blah, blah, blah. But now, before we make the system call, to tell the kernel which system call we want to do, we put on RAX, it's where we returned before. Now it's also where we want to, it's kind of like the dispatch for the command that we want to call. We put the correct number. So to call exit, we put the number 60 on RAX, for example. And then we put the error code that we want us to be returned on RDI. Okay, this is the idea. So, and then the result of the system call, we're going to read it from RAX again. So the system call will replace RAX. We take it. It first has a system call number, and then at the end of the system call, when the kernel completes, at RAX is going to be the result of our operation, if it worked, not, or whatever. Okay, so yes, right, we're going further down. So let's do a system call. Let's call exit. Okay, and I would like us to do exit with and return minus 13. Okay, so let's open exit.s. Okay, again, same things here, like global. I have a function called die now. Okay, and we're calling die. Okay, and we are returning 1337 here, but we know, this is not a good number. Maybe I should change it to, 13. Just okay. And I want us to call sys exit, the system call exit from the function die. Okay, but I have failed to tell you one more thing. Okay, you set RAX, you do the move, you set the registers. How do you do the system call? Well, there is an instruction called system call, right? You just write system call, and once you do that, it hands it off to the kernel, and you better have it set up right. So let's do exit. We said the system call number is 60. That's my first thing that I'm going to do. I'm going to say move to RAX 60. Okay, I'm preparing to call exit. What argument do I want to give it? Well, I said move to RDI, which is my first argument, minus 13, right? That's what I requested, right? Minus 13, yeah, minus 13, okay. And then what do? Does it have any more arguments? No, just one. Put it on RDI, 60, be good to go. What I tell you now? Syscall, like this. And you know what? This is going to return something back. So this, I'm not going to make 13. I'm going to make like, maybe, I don't know, 22, something this big. Okay, let's see what's going to happen. I'm asking you guys now, what do you think will happen when I check the return value of this? Let's think before we compile and run. What would the return value of this assembly program be? It's not an easy answer. So what do you think? Will it be, we have two options. Will it be minus 13 or will it be 22? We have it minus 13. Yes, minus 13. Okay, I'm right there with you. I think you guys are correct, but let's see. Make file exit dash asm, make exit asm. Let's do it. Exit asm. Wow, 243. Why do you think that's the case? Maybe. Plus, we got a big number, right? We got something bigger than 55 that we're in for. I mean, that's pretty exciting. Let's try to exit with a positive number. You know, let's make sure it's not this minus over here. Okay, let's try to exit with 13 and then 22, and let's see what this is going to do. I'm remaking the program. I'm running it. Okay, now we have 13. Okay, fantastic. Now, any takers on why minus 13 became 243? Why is it correct? Like, what? I got 243 from minus 13. It's not that hard, actually. It is yes, it is exactly signedness. Like the result, now we can see that kind of the operating system expects an unsigned character there. So it's ucar, what the operating system expects. We passed it a signed character, and of course it's, thought that the sign bit is something, something very large there, right? But not super large, because the maximum it can go is 255, because it still reads one character, right? So cool stuff. Okay, we're making some progress. We're dealing with the confusion here. Let's proceed. We have now made our first system call. Let's see, what is the next task that we have? Oh, now we're going in for some real fun. Okay. World in assembly before we even write it in C. Okay. There is going, let's see, there is we'll write hello world in assembly. There is one more instruction that I'm asking for you to look here, and it's called LEA, load effective address, or LEA, right? From Star Wars. Load effective address, it still gets me most of the time, right? I might put something on a register, I might try to use it, and then it's just some weird stuff. I'm like, what are you talking about? And then I remember, oh, I should be actually accessing this as a pointer, because I don't actually want the actual value. I want the pointer to that memory address. So when you're giving here, when you see like I want the pointer to the buffer to actually access the buffer, when you see pointers, like mentally in your head, say, okay, I probably need to use load effective address of that to actually get the pointer to that. Okay, this is going to come and like be important now, because we will need to do the right. We need to call hello world. We need to do right. Okay, and we will need to put our stuff on a buffer, and then we'll need to use load effective address of that buffer. Blah blah blah. And the instruction, the system call we're going to use, we need number one here, which means write the file descriptor. Again, we're going to write to the standard output, which is the file descriptor 1 here, and it's open for us, in Linux from before. So 1 is open. RDI should be 1. Just take it like that. Then we're going to put the buffer of what we want to write, and then the count of how many numbers we want to write. So let's check it out. Hello.s. Okay, I've done some work for you, and I've shown you how you kind of can structure your thingy here with the data, like your buffers, in a useful way, and how you can get the length of what you just typed here. I'm going to explain in a sec. What we need to write is over here. Okay, we're going to call hello. Hello needs to do the system call. We don't really care about the return address. You might consider this a void function, right? We don't care what it returns. So we just want to see hello hackers printed. Now, let me explain this. You see now we have one more section. Before we had only text. Now we have text and data, because we said, data holds the data of the program. And this is kind of static here, hello hacker. So we say we're going to call this MSG. And this DB means declare bytes. It's not database. It means declare bytes. And we're declaring some bytes. Okay. There are other ways that I could write this too, but I'm going to use this one. And then I'm going to declare some other variable here called size, sz, which is equal to the current address minus the starting address of MSG. Now, let's try to think about this. Everything in assembly is put in a physical address. So let's say this lives in address, 1. And this takes some space and goes from 1 to 6. And this lives in 7. Or, 6, like at the end of 6, right? Okay. It lives in 6. So if you take the address 6 and we subtract from that 1, we're going to end up with the number 5, which is how many bytes the thingy above takes. So this is a trick you can use to actually, calculate the length of the strings. Like if you declare them, then just get their length straight away. Again, this means the current address of this. So message and size, it's declared for you. And go ahead and write the system call right here. 256 minus 4. Yes, correct. Because this is the 2's complement that we see here. That's why it works like that. There are no more lights here because I'm becoming again darker. Sorry, I'm 1 hour ahead of you. Oh, no, I'm 1 hour before you. It's even darker. You guys. Okay, let's write it. So we are going to first call write. So we're going to move on RAX. Write is 1. Okay. And then on RDI, what is on RDI? On RDI, the first argument is the standard out. We said this is going to be 1. Okay, so move RDI 1. Okay. And then the buffer. Okay. LEA, because I told you we need the load effective address of the RSI MSG. So this puts the pointer, the address of MSG to RSI. So that's how we take the pointer. That's how we take this. And the count, we are going to do RSI RDX. On RDX, we're going to do SD like this. This should be good. And then we're going to say syscall. And I'm going for it, guys. I think this should work. Make hello ASM. Bam. Oh, we have some problem. Blah blah blah. No such instruction. MSG. Why? And what did I do? No such instruction. Why? Maybe I can compile it directly with GC. Let me see. CC dash O hello. No such instruction. Let's see. Let's see. I'm making a mistake here. Look it up. have to look it up. Whoever figures it out. Oops, the slide. Yeah, sorry, the slide. You want it right now? Or, I will share the slides, of course, afterwards. Here's the slide. Here's the slide. Yeah, because I'm an idiot. Let's go back. And this needs to be probably indexed with this and this. And let's see. No, why doesn't take the message? Whoever finds it. Wait, I can throw it into ChatGPT and ask ChatGPT because like I don't even remember what's the problem here. So, oh, wait, maybe I forgot. Yes, wait, I forgot. Maybe the problem is over here. Maybe it needs let's see now. And yeah, there's one place. You need some columns. What's the problem? Okay, I'm going to debug this in a second and come back to this because I don't want to delay us here. But let me see if ChatGPT has any point here. Section data, looks correct. MSG, it wants to offset that. Okay, dereference that. Okay, let me see if that's going to help me. So ChatGPT says that we need to dereference that. Let's see, but SZ should work still. Yeah, it doesn't. It's not a problem. Section.data. Don't tell me it's a problem, and it's this. No. Anyway, I don't know what the problem with this is. I will figure it out, and I'm going to let you know because of how I messed up here. And we figure it out. So, okay, yeah, should have compiled yesterday. And it's not global football, instead global hello. Okay, well, yeah, let me see. Yeah, but did you manage to fix the? Maybe you're correct. You're correct with that. Yes. And good point, but I don't know what is the problem with the data section. And let me try. Wait, let me try. Maybe it doesn't like the declare bytes, and I'm going to try dot ASCII there, which means ASCII and zeroed out. Let me see if that's going to make it feel better. This anyway. I need some time with this. I will figure it out. It doesn't work, but we'll fix it. Something with my assembler. Okay. May need to escape. Let us see what you mean here. Escape the. No, I don't. I don't think so. I'll remove it completely. But I don't know. You guys have ChatGPT there. Try throwing it into ChatGPT, and maybe it will give you something that I don't also have like here. But yeah, it's embarrassing, but it's fine. You know what is a live demo without some embarrassment? It's no fun. So we'll figure it out. Let me see again. I'll try to compile it. See it does. Oops. Uh, Red compile with GC, not with the GNU assembler, but I don't think that will work. Leave. So no, it doesn't like my instructions, the MSG and but this is in the dot section. Anyway, I evidently don't remember how to declare this as a variable instead of it tries to think it thinks it's an instruction, but it's not. So that's why I'm failing here. Okay, doesn't matter. You get the idea. That should kind of work. That's what we're trying to get out of here. Now, looking at hello, I mean, I have a C hello world right in there. You will see I have a C hello world. Where is it? I lost my VM here. Just a moment. Come on. Yeah, this is the VM. Sorry, and I have this this hello world that is the what we compiled from the C program, and the C program, as you expect, nothing new here. The C program is just this. Okay, it says printf hello hackers. Okay, now if we disassemble it again, as I'm showing you here, make hello for this one, and if we disassemble it and we go into the main function, we will see that I said to you that it's going to be a system call over here, right? But I don't see any system calls, right? That's what I want you to point out. Then you're like, okay, maybe the system call is in IO puts, right? And you'll go there and you'll see that, oh, the system call is not even there. So what I want you to know is that sometimes system calls are hidden, and in this case, the system calls are hidden into functions that are, they're called something v blah blah blah, and they are functions relate to the file descriptor. So you don't really see the system call happening up until you follow all these crazy, layers of functions over here. Okay. And finally, we can get into GDB. So let me see any questions. But you mean if what is common for system calls to like be hidden further, further down the execution? Yes, it is. It is pretty common because in the end, here libc is doing all the system calls, right? When you compile a normal program, so they are hidden always in libc functions. You wouldn't expect that a normal program would issue directly a system call. That would be a good indication for maybe someone's hacking you, right? Or you're running shellcode. For that reason, a lot of operating systems like OpenBSD has mechanisms that only allow system calls to be called from certain places. That can reduce the attack surface for a program. Now, let's do some GDB because GDB is super important to be able to do to understand what's happening. I'm giving you here, I have written certain. First of all, anyone, you guys have done in GDB? Like Toblerone, maybe Nikki, like you guys have done. Okay, awesome. I don't know if. Okay, cool. So let's. I like Jeff or Jeff too. I love it. But and you will have it installed on the container. But here we can work with some basic GDB before Jeff, right? What I want you to know is, I think I've written most of the stuff that you might need here. It is how to break on a function or an address. Okay, so we set a breakpoint. Now there is a question about it, how a breakpoint works. What do you think is a breakpoint? Any ideas? And how breakpoints are implemented? Trying to remember which. So a breakpoint is actually an instruction. You replace an instruction with the instruction int3, and when the system sees that instruction, it knows to stop the execution there and give back control to the caller, right? So the person who is tracing that. So breakpoint is a specific instruction called int3, and you can actually, if you take a binary and you inject that instruction at a point, and then GDB is going to break there. Okay, and it's pretty funky. And that instruction, it's a byte, right? I mean, you find that value of the byte, what int3 is in x64, and you put there, and it's a breakpoint. Now, this way you can put the breakpoint. You can examine memory. Okay, x/format here. I'm telling you, so you can examine memory as words, giant words, strings, or instructions. Okay, and other things possibly, but these are the things I use most. You can see your registers by info-reg. You can see the frame of your function by info frame. You can see the segments of things that are mapped, by info files, backtrace, and you can step an execution. You can disassemble a function like what we've been doing. GDB is amazing, right? I mean, I personally, I love dynamic debugging and dynamic, reversing with GDB. So, we have this debug binary. Okay. Let's fire it up in GDB, first of all. Okay, so we're going to do this together. Let's make the debug binary. First of all, which, sorry, here, yeah. So I'm going to say make debug. Compile the debug binary, and I'm going to fire it up in GDB. And I'm in GDB with the debug binary. And it's not running right now. Okay, so if I say, nothing is happening. I haven't pressed R to run the binary. So I can examine it. I can say disas main. And I can see the disassembly of the main function of the binary. And I see it calls something here. It calls like malloc. So it does a malloc. And then it calls something called catch me. And then calls free. So what I want you to do is I want you to put a breakpoint on catch me and try to catch this function. Okay. And so yeah, we're getting there. So let's put a breakpoint on catch me, B, or you can say break, but you can also say B on catch me, and you can press tab and it will complete for you. So we have a breakpoint at this address, it tells you. Okay. And notice the addresses are pretty short here. This has been a non-pie executable, so the addresses, are pretty short. So I can say info breakpoint, and it's going to tell me, yes, you have indeed a breakpoint on catch me there. So I'm going to press R to execute this program. And it runs, and I broke on catch me. Okay. Now, please notice something. Okay. When I ran it here, it wasn't executed. So I was just seeing kind of the offsets from a virtual zero address that the program has. But when I ran it and it was loaded somewhere by the operating system, and it was loaded in a place that gave it the 0x555555 blah blah blah. So the actual address that got when it's loaded is 5555, but you see the 414D. This is the same offset that it has kept here, like 14D. The one, was probably used because that would be 4 if that one was not there. I hope you see that this distinction here. This is before it was run, where it has no context of where it's going to be actually placed. And then after we ran it, where it knows where it was placed, and it broke at this specific place. We are in this function. We say info frame. It says, okay, you're on stack level 0, blah, blah. I write disas to disassemble and see where I am. And I'm in catch me. Okay, I'm in this function catch me. That's what it says. And I'm past the prologue, as we said. It has already done the push RVP and move RSP and RVP, as we said before. We're in the first instruction of catch me after, after execution. So remember, we said we can examine the arguments of a function. So let's see that by saying info registers. I can see what are the arguments of the function. And I know the first argument is on RDI, and the second argument is on RSI. Okay. The first thing I want you to notice is that RDI is on 0x777, 7FFFF, blah, 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 and RSI is on 0x55555, blah, blah, blah. Okay. Well, I also told you about another address, see where everything is mapped, which is info files. It's big, but we see that the stack here, if you see like where does it say stack, it's pretty big. It's bigger than I expected. Where is stack? Stack data should say somewhere. We should find the word stack here. But anyway, you would see that stack is on 5555, and here let me do again info, right? This is RSI is RDI is the stack on 7 blah blah, and this it will turn out to be the heap. Because remember it did a malloc before. So let's examine this memory as with x slash, I'm telling you it's strings. So I'll do x xs on the RSI register because I want to examine this, the RDI, the first register, and RDI, the first argument. I'll do it like that, x slash xx $RDI. And it says just an arg to catch me because I examined it as a string. I can examine it as bytes, right? Let's see. And it's going to be like 20, 60, 61, 20, 74, 73. This kind of should hint you that this is an ASCII string, right? And all these characters. But if I examine it as a string, it says I'm just an arg to catch me. Or I can examine it as many characters. I can examine it as, like, for example, 15 as 15 characters. And this is one of them, all printed together, like, G, J, U, blah, 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 blah. Okay. So, okay, that's pretty cool. I examine the first argument. Let's examine the second argument as a string. I will examine it as something like that on RDI. Yeah, RDI was the first and RSI was the second, just another arg to catch me. But we see that RDI is living way further down, right? It's living heap. Now, I will load the program over here, and what is it? This program is called debug.c, and let's see it. Okay, main makes an allocates a static buffer here and says just an arg to catch me, and then it's also allocating a string in the heap by malloc, and it populates it with this thing called just another arg to catch me, and then it calls catch me. Okay, and then it frees the heap thing. Now, we said RDI is the first argument, this one, right? But then we also see that catch me has its own little memory allocated in here. So let's find that. Okay, so I'm going back here. I'm again doing XXS on RDI. verifying this is the first argument. This is just the first argument to catch me, and I print more strings, and so I did that. Now, let's see. This is on this address. Okay. What is on the, if I do info array, where is the stack pointer of this function since we're in catch me now? Where is RSP? RSP is on 7FFFF. First of all, it's still in the stack, like 7FFF is a stack now. Okay, let's close the stack. The argument was on D950, and now we're on D930. Okay, the argument here, D930. So let's examine this. Let's examine as a string RSP. Okay, it doesn't show a lot. Let me do 10 access. Doesn't show a lot here. And if I examine way further down, see. My question is like, where is this argument over here? How can we find this argument? And also, let me make sure that I hope you guys are just playing around with GDB and just trans and stuff now. I mean, this is just again. Now, I think I know why we don't see that argument there, because I think it never put it there because it was optimized out, because we never compiled it with. We actually just, the compiler said this argument is doing nothing over there, so I might as well just be able to be done with it, like ignore it. So let's see if we compile it with O0, which is no optimization, if we're going to change its mind. So let's declare this, copy, debug, and debug, and then the on catch me, and then R, and that one catch me, and I do X, then it says on RSP, and I still can see my argument. I don't like this. And look at the stack for the why it hasn't. Well, look, it hasn't put it there, and I don't know why. Okay, but what I want to show you here is that this is the beginning of my stack on RSP here on this catch me function. Okay, and we're on this catch me. Let me check it out for a moment. Now, I want you to see what happens. This guy has a 512, 512 space here on the stack. You know what? I'm actually pretty angry by this. So I'm going to stop it again. And I'm going to go back here. And I'm going to just not set this statically. I'm going to memcpy, this thing, or strcpy, so over there, because I want to see, because I'm pretty pissed. So instead of doing this, I'm going to say, okay, car f blah 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 equals 0, so it was 0 on the memory, and then I'm going to say strcpy on f, and I'm going to string copy this whole thingy here, and I hope that this should work like this. Again, like demos. Okay, I'm going back here. I'm doing GDB debug. I'm breaking on catch me. I'm running, and I'm doing. Now let me see. Maybe it hasn't executed yet. Oh, I didn't think of it. I'm doing this as. Okay. Yeah. Maybe it hasn't executed yet. So I need to actually. Oh, yeah. I'm an idiot. Look, sorry. You see, like when we look at catch me, we see like some stuff over here, like this as. You see all these things over here that it's moving something blah, blah, blah. It's very possible that this is the string I just want to move. And you see this 696874. This looks like ASCII. So the compiler did something funky here. Observe what the compiler did, right? And this is a no optimization thing. The compiler just probably took all the string that I wanted and made it into, put it into registers, and then is writing the registers directly. So let's move up to here before this, let's break over here and break on catch me at the end of catch me plus 153 right before it ends here, this leave, and continue. And now let's examine the stack. Again, I don't see anything. Maybe it's the ball. Why is it? It just destroys me, this demo. I don't know where it is. Anyway, I don't know where is the string. I'm sorry for that again. But what I want you to see, like from this, the important thing is like I don't have it yet. As you see the stack over here, blah blah blah. Further down, we see some addresses. Okay, that's what I want to show you here. And we're in catch me. If we run BT, which backtrace shows us who called us. We're in catch me, and we were called by main. Okay, and main, this is the saved instruction pointer that we need to return back in main, and it is 5555 to B1. So I want you to look over here and see that over here we see 55555 to B1. Okay. Now, and I'm telling you that this space here is 512 because that's the amount of space I allocated in catch me. Okay, I don't know why it doesn't have my stupid string that I put. I honestly, but I can tell you that back here, like after 512 bytes, it has the base pointer, the saved base pointer, and then has the save instruction pointer. And let's verify that. So we're going to examine as a great word RSP plus 512, and we should hit this thing now. No, maybe alignment 520. No, 528. Damn you. What is the difference? 536. We'll never make it there. How far does it go? Why does FAS allocate so much memory? What is that distance? Okay, we need to calculate that distance. We are going to calculate the distance from this to that over here. Okay, so we want D798 minus D938. D798 minus D, what was the other one? D938. 416. 16. I don't know why it has. Yeah, I don't know why. I can understand why it does that right now. Okay, why it's not 520 and it's 416. It might have done some stuff with the string I put there, and which I never see printed, and that's why it reduced the 520 to 416. You know what? Let me break once more in the beginning of this function so that because I'm pretty persistent about this. Gotcha. But I would expect to be on 520 because that's how much space I have calculated. I have allocated. And let me do again x 100xg on RSP and to run. Okay, so RSP is now up here. This us. Where are we? We're here. Okay, it's going to. Yeah, it hasn't. Okay, it needs to run this command, so it allocates space. So we're going to step with this. Now let's print here. It has like all that stuff. And I want to see how far down the saved instruction pointer. So I will do I will do 10xt rsp plus 512 because I know that it should be around there, and I see nothing. I don't know. I don't know what's happening with this optimization with this function. This is the return address I'm looking at, and it is not on 512, but it's on 400 something. What is it? 400. Yes, it's on 400 something. 421 over here. This address. I don't know why, but I don't need to know why. In the end, I mean, I should really figure out why. But what I want you to see and what I want you to try to understand is this process here. You go into a function, you look at the stack, you look past the end of the stack, and you try to find the saved instruction pointer. And what is the saved instruction pointer? It's this thing that you see from the backtrace. Okay, so you know that you're going to have to return back to something called 55552b1, and you want, by looking at the stack, to see where that saved instruction pointer is, and what distance is it further than from where you are writing. Okay, this is the important thing that I want you to keep from this. Okay, so when we're in a function that has a vulnerability, we do backtrace, we see the saved instruction pointer, what it is, and then we look at the stack and we see how far down do we see it. Okay, we see it over here, and then by seeing where we write, we can kind of calculate how much we need to write to overwrite this guy. This is the idea, and I need to see why it's failing, and to behave as I expected. But anyway, let's continue. Okay, so examine the stack and segments, blah blah. Okay, we're in the second level. In the second level, they are the lustful and the people who don't have any patience, and they're being carried away by winds. And this is a painting by William Blake, which actually, I think it's the same William Blake that is the poet. But I might be wrong on this one. But it's a pretty cool painting. So let's gain read control finally on a program. Okay, let's do it on a program that will not behave so badly, as we said. And now we have this program called bufo, which is a buffer overflow. Okay, and our task is to send large input to buffer overflow, and we want to be in GDB and see what happens. Okay, let's first examine the program so we know how it looks like in terms of sorts. And I'm going to read GDB here, and I'm going to go over here and see bufo.c. Okay, so this program has a main function that calls challenge. Challenge allocates a buffer of 512, fills it with zeros, printf something cheesy, and then reads 536 bytes. Okay, on that buffer. That is more than what the buffer has. That should overflow. Okay. It also has another function called unlock. Now, our first goal is to just overflow the instruction pointer for this program. But let's first compile it. So we do make bufo. We compile the program. The compiler is pretty good. It's like, dude, you're in for an interesting time here because you're writing more than you should. We completely ignore the compiler because who cares about correctness? And we run GDB on this program. Okay. We run GDB on this program. We do disass main. It's like, okay, you call chal. We're like disass chal. We go into chal, and let's break. You see like this. You see this 200 straight away. I know this is 512, right? Because 200 is 512 in hex, and so I'm things are okay. Things are making sense in this program. I don't know why the other program just makes fun of me. I need to think about it. But let's go and break over here, break on here, approximately after it has allocated the space. Let's break on chal plus 18. So b chal plus 18. And you see, I can either break on an address or I can break like using the pointer. I can say pointer, the name of the function, and then an offset. So b start chal plus 18. Breaking there, running the program. Okay, and I broke. I'm right where it kind of fills the memory with zeros, right? And it's going to fill the memory with zeros, and you see this REP instruction. This means repeat. Okay, repeat store, and it's going to think the instruction zero out the memory. So I'm here. Let's see if there are any questions. I hope you guys are William Blake. Yes. Yeah, pretty cool code. So we're here. Okay, let's see how the stack looks like. So we do x10 xg, for example, on $RSP. We see some stuff. Let's do 100 xg. We see a lot of stuff. Okay, we see the stack, blah, blah, blah. It has the stack has stuff in there. But what did I tell you? I care about where the return address is. So I'll do a BT, see how my return saved instruction model looks like. And I know I will eventually have to return back on 4018B7, 4018B7. And then I'm going to look here and try to find this. Where is 4018B7? 40 should be 018 B7. Oops, there it is. 4018 B7. There. And my stack starts from whatever this is and goes up to here. This plus 8, because this is this, and this plus 8 is this. Okay. Let's calculate that distance. So we have D940 against DB48. DB48 minus D940. We go in Python. We're like, okay, 0x DB48 minus 0x D940. 520. It says the distance is 520. Let's make sense of it. It says that from the start of the stack till the start of where the instruction pointer is saved is 520. Does that make sense? Yes, finally, because we allocated 512 bytes over here, plus 8 bytes for the base pointer that's saved. That's 520. Okay, so it makes sense, right? We finally make some sense out of it. So if the moment I write 520 bytes, when I write 520, nothing has happened. When I write 521, I have overflowed 1 byte of the instruction pointer. Okay, so let's try something here. Are we following until now? Are we following? Yes, no? Can you guys kind of at least, not do exactly whatever? Okay, good to go. Okay, so what I'm going to do now is this program reads from stdin. It will read 536 bytes. So I'm going to give it enough bytes to overwrite its instruction pointer. Okay, I'm going to go here and I'm going to say, okay, A times 528. That should override the whole instruction pointer. Okay, because I'm going from 520 to 528. I'm taking this now, copying it, going back to GDB, and I will say to the program to resume execution. I'll say continue. It says I'm overflowing with joy, and it waits for some input. Okay, and I'm going to give it 500, how much? 528 A's. Let's see what's going to happen. Oh, it says the program received the segmentation fault. Okay, and if I do info-reg and see the registers, look what is happening with my base pointer. My base pointer is 41, 41, 41, 41, 41. And my instruction pointer is also 41, 41, 41. And that is it, although it doesn't show it here. But this is why, because the instruction pointer is 41, 41, 41, it never actually managed to use that value as an instruction pointer. And that is why it has a segmentation fault, because it tries to see where that memory is. And it's like, I don't know where that memory is. You know, it's not mapped. And that's why I'm giving you a segmentation fault. Okay. So this successfully overrides the instruction pointer. Now, what would happen if I only gave it, you know, if I only run it, for example, and I only give it $520, so I removed 8 characters, it should be okay. It still crashed with a different instruction now. It says sig illegal instruction. And if you can manage like to figure out why, it's because I still have overwritten the base pointer. So when the instruction returned and tried to do its thing with the base pointer, it still, you know, went to an illegal place and fetched the instruction from there that is illegal, and that's why it gives you illegal instruction. Okay, if I still run it once more, and I just give it, you know, so now I'm not, I took 8 off and I'm taking 8 more off. Now I should give it like 512 and it should be good. Well, it still got an segmentation fault. Why? I don't even know. Yeah, maybe because I gave that plus the new line. But anyway, how much is it reading? 5. Let me just put 512. Yes, continue. I'm going to Python because evidently I cannot count. I'll let Python count for me. And I'll do this times 512. No, 511 plus the new line. And I'm going to do this. This should not crash if everything goes well. Taking this guy, copying it, going back here, pasting it. Okay, it did not crash. It exited normally. Okay, because I wrote this bytes plus the new line, and we're good to go. So we managed to crash the program. So I want to override the instruction pointer and put in the address of where I want it to go exactly. Okay. Now, here's what I want you to do for this task. I told you there is another function here called unlock. And in GDB, I want to see where unlock is. I want to say this as unlock and see where that thing lives. Okay. And I know it lives on address 401845. That is where unlock starts. Okay, that's what it tells me here. Okay, let's run once more the program. All right. I'm breaking in the beginning of challenge here before I read. Okay. Now, I'm doing backtrace. This thing should return back into 4018B7. Okay, where main is. I want you to make this guy return back to 401845 instead. So I want you to make this guy return to unlock instead of main by overriding this pointer. And if you think about it, all you have to do 1 byte, because if you examine over here, the stack, and 100, sorry, and you see where this thing is persisted down here. We said 40 blah blah. What was it? B7. Where is it? This B7 lives over here. 4018 B7. If you override this last B7 to what is unlocked to 45, then you're good to go. So I want you to come up with an attack plan. How many A's you need to send? I want you to send A. And in the end of AA, I want 45 instead to override that P7 over here. And there is a problem here because when you send it, you're also sending new line. So that's a problem because you need to press enter. So how are you going to deal with that? That's also a question. How can you send the bytes without sending a new line? Any takers on this problem? Python is a great question. The answer to everything. A great answer. The great answer. Yeah. We can do it without Python too, though. I mean, if we're going to be really fine too, but we can do it with Python for sure. Okay. How can you do it with Python? How can let's work on it. How can we do it? So essentially, I want us to write a bunch of A's and then one byte, and then somehow redirect that to the program without a new line. And if we use like the redirect character, this, we should be good to go, right? So we'll just make these bytes, redirect them. But you know, are you going to do it with Python, with hex editor, with how are you going to do it? With printf, there are many ways. Okay, how are you going to do it? Everyone can do it however they want. But okay, before we do it, I want us to have an attack plan. I want us to all agree how many bytes we're going to write. How many bytes of A's are we going to give to this? 509. Why 509? Okay, let's go back here. We see the stack. We are starting to write here on D940, and we see our target is back down here, right? This is B7, right? This is main BT. BT, yeah, it's this B7. So we have D940 and the distance of DB here. Look where this guy is. It is here on DB40 on the second column. So it's DB48. So we want this difference. DB48 minus D940. Going back to Python, I have calculated. DB48 minus D940 is 520. We're coming now. Now I see plans. Okay, 509 plus 2 bytes for the address. No, this 509 won't work. It has to be 520. I'm arguing because that is the distance, right? We see that the distance. Maybe I haven't persuaded you in this because this to this, which is our target. Python says if we do this subtraction, says this 520 apart. So first I want us all to agree that the target has to be 520 afterwards. And yes, okay, so yeah, so this is a yeah, Barkab has a potential attack here, 520. It cannot be 509 because 509 is still within the 512, you know, that is this buffer that we have allocated, right? If you do here, you know, this plus 509, you're going to end up somewhere before where the instruction pointer is saved, somewhere, you know, in this stack. So it's going to be fine. And the buffer is 512, yeah. So the buffer is 512. Then we have the saved base pointer. So after the buffer, we have the saved base pointer, which is, where is it? 7. This is the instruction, the saved instruction pointer. This is the saved base pointer. This here is the end of the buffer. This would be the end of the buffer. Then we have the saved base pointer and the saved instruction pointer. So up to here is 512. Then it's 512 plus 8. Okay, we get up to here to the beginning of this. So 520. Yes, 512 plus the size of BB plus. Okay, Barkab, I think you're into you have something here. Let's try your thing. Okay, so you say Python print 520 plus 0x b7. Let's try it. Okay, I did it. Yeah, I'll just copy paste it because that's what you do on the internet, right? Uh, I will stop being in the debugger here for a second. I'm going to see like Barkab's Python program is this, so that we can all see. It says it probably also needs one more parenthesis, and then it's close like this. He says 520 blah blah plus this b7. But wait, Barkab, b7. Look, b7 is where we're already going, right? b7 is what it had already. So right now you're not going to do anything. Right? So maybe you want to point it to the unlock function, which is, and look, this doesn't look like this hex is correct, right? Maybe you want to say b here and then say 0 x b7, something like that. Would that be correct? No, b, how do you do it? Backslash x b7, sorry. Yeah, that should be correct. But no, it's not b7, we said. It is where the unlock function is. Yeah, we would be overriding BP, and it's fine to override BP for now. So going back here, let's find where the unlock function is. This as unlock. It is on 45, you see, not B7. B7 is where main returns. B7 is look where main would return after the call to chal. You see? So 145 here. So your thing should be 45 here. Okay, actually the letter E, which is convenient, right? So we can just have written I. Okay. So, okay, if we do like this, we make this into a shell and we pipe it to the debug program, what's going to happen? File name too long. Yeah, because yeah, we want it. Okay, yes. First, let's save it. Save this output to a sorry, save this output to a file, or you can just pipe it and to debug. So I can pipe. Say to reload and then do debug. It printed nothing. And okay, let's run. Sorry, we're not doing debug. We're doing bug. So, okay, I'm overflowing with J segmentation fault. Then, interesting. Why did you manage to have it execute? But why should I do it in GDB? I mean, I can. So let me do it in GDB. GDB. Okay, I'm going to run. I'm going to go here back on Python and say I want 520 A's and an E. I'm going to put E in the end manually. Okay, taking this. The new line is going to get me now. It's going to have the new line as a, it's going to be a problem here. Okay, and we're going to see why. When I put it here and I put E here, this new line is going to kill me. Okay, there is a way out of this because I will press now, it will crash. Okay, you see segmentation fault. And if I do like info reg, and it hasn't, where's read? Yeah, it hasn't. It hasn't. But there is a way. There's a way out of this. This guy reads 536 bytes. So what if I encode the whole pointer, right? What I know where it wants to go. I don't have to just override just one thing. I can override the whole thing, right? So your idea was correct. What if I, instead of just putting one byte there, I put the whole, you know, and where am I? No, the I go before the call to read, child plus 64, info RSP. What am I doing? Okay, now look, after the zeroing out, the stack is nice and clean. So everything has been zeroed, nice. Up until here, where is the instruction pointer, right? So this guy reads 536. What if I give it 536? I do the whole, if I write the whole thing. If I write this value in Python. Yeah, I see here. But you can't really see it because it doesn't. It just has a segmentation fault at this point. You see what I'm saying? So it tries to access in the segmentation fault, which kind of sucks. So you can't really see the value there. You see the base pointer. So I will try to override this whole thing from Python, and I'm going to use what's called pon tools. Okay, so I'm going to say, and I'm going to show you in a second pon tools. I'm going to say from pon and import star. And then I'm going to say, okay, I want you to print me these bytes, 520 plus a P64, a 64 byte of 64-bit character of where I want it to go. And where do I want it to go? I want it to go on unlock. What am I doing? Yeah, no, I'm not going to do this. I want it to go here, 0x401845 here, 401845. This would be it. Okay, in binary. These bytes. Okay, so let's take these bytes now, Barkab, and put this at the end of your Python buffer. How about we do that? Okay, as it what Tontil said. So we take these bytes, we go back here, let's go on the right side, and we're going to create, actually we're going to do it directly. How did we create that Python thing before? Like this. But here we're going to say this, these bytes, which is the address that we want to go, the full address. Okay, and this we're also going to make it into bytes. We're going to say bytes time and blah blah and bytes, and we're going to write that on payload. Okay, let's hex dump the payload. Blah 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 blah, and over here, oh, we still have this annoying new line. You see that we have the new line here, but the new line now is further out. It shouldn't be interfering with our instruction pointer. So I have high hopes that this is going to actually work. So we're going to say bufo redirect payload. It didn't. Why? Because maybe P64 is not little endian. Context dot no, it's correct. It's the same. And E. Let's see. Well, you know what? Let's attack it directly with pawn tools because this is pissing me off. Maybe this print has a problem. Yeah. Sorry. So yeah, my Python has a problem. You see, it's actually printing B here, 62. This is wrong. I wanted bytes, but it's just I don't want to print this B over here. So maybe this would be correct. No, yeah, I can't concatenate bytes and strings. Come on, guys, I have a Python problem here. I won't print it at all. I will just say B this plus B that. One minus. Honestly, sometimes I hate that. Okay, let's hex dump now. Hey. Okay. And takers. And takers on this. What should I write with Python? I want to just write the byte of A times, and let's try again, print this times this cat. Sorry. Okay, this, yeah, you see it's still writing B here. I don't want to. You see, it's literally putting B over here, but I don't want it to do anything like that. Okay, maybe just move this B. And it says can concatenate bytes to string. So I thought that's how you declare this be a byte. I'm having a Python problem here. Whoever wants to tell me how to make a, okay, you know what? Screw this. I'm going to say B x41 because I know this is A. How does it feel now? Okay, well, it's still got B. I don't know. Does it work now? Wait, let's see. This could be correct. 41, 41, 41. Okay, I just took the B's out, and but I thought so you need to give it bytes. So let's put that in payload and put it back into. Yes. Yes, it worked. Okay. Now, and this actually makes a good point of why we've used pawn tools, because we don't want to deal with all that stupidity, okay? Like with new lines and blah, blah. So that's what it's part of what I wanted to tell you here. We suffer in order to be able to actually use pawn tools in the end and have things actually work out. So look what happened. When we gave this payload, we managed to direct it to this function says here, you got a coin for your read control. And then legal instruction. And again, look at how we create the payload. Print and text for A 520 times plus, and then the 8 bytes of the pointer. So we wrote all the instruction pointer, and the new line that we put afterwards never mattered because it was afterwards. Okay, so it went to where we wanted. Okay, we wrote the whole instruction pointer. And yes, use pawn tools. Okay, remove being both with. Thanks, guys. Yeah, sorry, and I don't know why I thought B is necessary for bytes, but anyway. Well, we have it. We actually did divert the execution of this program. Okay. Yeah, and you can. You could, like, that's how you can also, instead of printing A's, you can print the no operation, like, the byte that is no operation, which is a hex 90 and does nothing, right? So the face, even if it jumped there, it would be like no operation, hex 90. Okay. Now, Finally, in this program now, we just diverted it to go somewhere else. But what if we don't want it to go anywhere? We just want to inject more code into it. Like put our own code in the program. That's what we call shellcode. And traditionally called shellcode because we used to run it, and have it execute a shell for us so we can do stuff as a root, right? As the user of the program that was executing. So I have written this little assembly file for you called rflag.s. Okay, so let's check it. And this assembly file reads the file in /tmp/flag. Okay, it's going to read that. Okay, it's going to allocate a stack buffer of 64 bytes. It's going to open that file, read 64 bytes of that file in that buffer, and then write that buffer to std out. Okay, and then exit. Okay, and by the way, from this we kind of saw what mistake we were doing before. I didn't have these columns here, and it's ASCII Z for this, so we can go back in this debug program. Sorry, because I was pissed off. Back. Sorry, on this debug, not it wasn't debug, which was hello.s, and say this, and then I did this mistake here, and then sz should be this, and let's see if make hello asm. We still have this problem with this instruction because it's .pq. And anyway, hello will never compile, but we dropped it to one mistake now. Okay, wait, you know what? Screw this. How big is this? 1, 2, 3, 4, blah, 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 whatever, like 10. Okay, there. Done. Okay. Yeah, and say that's a number. Forget about hello. It's cursed. But anyway, where was I? On this R flag. This is assembly to read the file tmp flag for me. So let's go and populate that file. I'm going to open it. And I'm going to write, yeah, I have it, flag, Okay, so if I make our flag, and then I run our flag, it prints me the flag in /tmp/flag. So it says Fantastic. And then it is cursed, yeah. So now I have assembly to actually read a flag file. And what I'm telling you here in there is like, remember, this whole thing is now a whole ELF that has all the sections and all that stuff. How can I only take the actual shellcode that I want to run? Well, you use this thing. It says objcopy, take the text segment and dump it into a file. So let's do it. Objcopy and dump section. And take the .text segment and put it in, shellcode-raw. And then I need to give it the file, which is our flag. And now I have a new file called shellcode-raw, which I can inspect with hex dump, and has the instructions, only the instructions that I wrote in assembly that actually do that thingy without the rest of the ELF file. Okay, that's useful. Keep that command. You might want to use it. Now, your question, like, if I could write C and then go and do that, no, it wouldn't work because C would have to do calls in libc and all that stuff. So that's why I wrote the whole thing originally in assembly, right? So it's only certain instructions, it's only system calls. I don't have to deal with it. Would deal with having things, in an allocated, and need the whole ELF there. Okay, so these are the instructions that I can have it read that flag. Theoretically, if I put these instructions into the previous program, okay, and I jump to these instructions, I should be able to read the previous program. I don't know if you guys agree, but this is, yeah, let me know if you guys agree or if you guys are freaking out, whatever. Let me know how this sounds. But our attack plan is this. Okay, our attack plan is to put that stuff into the buffer and then go and overload the instruction pointer to point back into our shellcode. And then maybe, we can put some nop if we want, we can put some no operation. And that's useful sometimes when you don't know exactly where you're going to land. So you put nops, so that's called a nop sled. So you can hit somewhere in the nop and just sled down, right? And then we will run our shellcode. And our shellcode now is this, okay, what I gave. So I have given you some head start on this one. The cat is very hungry. Go away, cat. Go away, you little later. So let's do it. Shellcode by using I have a little Python program for you. So now things finally start becoming more sane. I have a Python program called bufo-solve.py. And I'm using Pontools, and this is, the beginning of how you use Pontools, okay? And I'm just showing you some stuff, like if you can fire up GDB from Pontools, and we have this thing that says with process, blah, 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 as this. So I'm opening a process of the program, right? And I name it P, and then I'm also reading the bytes of the shellcode, okay? The thing I just extracted with objcopy. Okay, and I name it payload. I'm reading this payload bytes. Okay, and then I want to send this payload in the program using send. The p.send thing here. Okay, now a beautiful thing that you will see with Pontools is that this will not put any new line. It's going to only send the bytes, right? Which is pretty cool. It's not going to infect us with a new line. So all we need to do for this to work is to complete this one line that I have here with the payload that's commented out. We will need to make the payload our payload byte plus padding plus the return back to our payload address. So let's talk about how we're going to do it. What are we missing? What are we missing here? How is it need to complete this? Know where the address that we want to land back is, where our payload is going to be stored. And to do that, we just use GDB. Again, we'll use GDB away. We're going to disaster. We're going to stop right here, the read. So we're going to break at chal plus 64. 64. We're going to run. We're going to examine the stack. And we know it. This is going to be where our shellcode is going to end up. Okay, this is where it's going to start. But just for proof, we're going to just give it some bytes. So I'm going to press NI to step over it, to actually run the instruction and stop afterwards. I'm going to give it a, and then I'm going to print the stack again. And look, I have a and then that unknown new line over here. Okay, and indeed it starts writing my stuff over here. So you got it. We have the size of the payload. We have where we are returning it in. Okay, so let's start putting this together. I'm going over here. Do we want to put any nop or not? What do you guys think? I say no nop in the beginning. What do you guys think? Let's keep it simple. Nop bytes or A's, shellcode, and return address. Let me ask you something. Why don't we do shellcode and then nop and then return address? And we jump straight to shellcode. Not that. Why do we start with no? I'm arguing that we don't have to start with no. Have done this workshop with open mix, so we can all talk. The execution order goes like that. No, so okay, let's think about it. We'll try both. Okay, and we're going to put some stuff in the buffer. Okay, then we need to fill it up to where we hit the instruction pointer, and then make the instruction pointer point back into here. Then once we're back into here, we start executing the stuff we put in. Now the other option, as you say, is to put nop, then the shellcode, and then the final payload. So then we would go, then the read. So then we'll go back here, do nop, and then hit our shellcode. And the execution order goes like that. Maybe you want to talk a bit more about what you mean by that, because I'm not sure. But again, I'll start writing over here, and we can work with it. So I'm claiming that we can first put the payload bytes, the things that we just extracted in shellcode-raw. Okay. So we put the payload bytes. Then we need to put some fluff, right? Some crap here, some irrelevant thingies. So I'm going to put knobs. How many knobs should I put? How many knobs should I put? Remember, in the end, I want to hit that, the thing, I want to hit the return address at 520, right? I'll be hitting that address at 520. So I'm putting the address here, the actual address that I took, that's the start of my buffer over here. So now my question remains, how many knobs do I put, or how many A's, or how many, flat do I put in here? 520 minus 8 minus size of shellcode. Why minus 8? The return address is right here. We have 520 till to get there. So these two together should be 520. Sense. These two together should be 520. So I'm going to say these are going to be 520 minus LP, which is the size of the length of the payload. But I can try it with yours too, and you will see that this is actually going, if you do yours, it's going to override the base pointer with the 7FFFF. Okay. 520 minus payload, not payload minus 520, but yes. Because the payload is smaller than that. Let's try it. We're game. Let's try this straight away. Again, I'm opening the shellcode bytes that I extracted, the program, and just sending that the program. And then this interactive is just going to show me what the program does and allow me to give stuff back into the program. So I'm going to kill this, and I'm going to run Python print bufo solve. Okay. Didn't work here. Let me see why though. Reload bytes. That's correct. And then we put 90s and 520 minus LP, and then 5940. Could it be that this is just an address that has on GDB? Let's see. I would expect this to work. How much payload does it send? 122. Okay, wait, let me make sure that the payload works first. Let me do something here. I'm going to say shellcraft dot cat going to flag. So this is generating shellcode for me, and then I'm going to so I'm going to say like np equals shellcraft, and then assemble that. Look what you can do with content. You can write something, so they have like, you can actually cut a file, you can assemble that on the fly, and then you can also, just send that directly. And let's see if this is going to work. Oh yeah, sorry. This should be we're still not getting it. Let me see. Could be that if you are correct, we need 520 minus what was your point? Maybe I'm messing it up here. 520 minus 8. I don't think that's correct. I'm arguing that the address is not correct. Let me try to send it back to where it was before. Where did we want it before? We wanted it in what was the other address we had for the other function? How is it possible? I think I tested it yesterday. Let me see. Because I think I tested this yesterday. I'm starting to question my own sanity here. No. Why isn't it working? Is that the correct address? Yeah, I'm sending it on the correct address. Let me put the cell. Yeah, let me flip these guys. So I'll put the knobs first, and then let's see if we land into knobs. Maybe that will help. But I have a sense that the reason that it's not working. Yeah, the reason that it's not working is not that. I have a sense that the reason that it's not working is because the stack address you have is wrong. Because I know why. I think I know why. Wait, let me see. Cat prog and this kernel randomize. No, it's 0. And I have compiled it with. Oh wait, have I compiled it with non-executable stack? Vi makefile. Yeah, zexec stack. So it is the stack is executable. Why aren't we jumping the right place? Okay, I'm going to follow it in GDB. Sorry, I'm pretty tired myself, evidently, and this is what's happening. I'm going to keep this shellcraft here, so I'm going to generate this payload. Then I'll put some. I'm arguing that this address here is wrong on the stack, but I don't know why. Okay, just child. If anyone, because I can see the chat, if someone finds it, just shout. Break on child plus 64. Okay, go. We are on child. Examine the stack. Let's do RSP. It is on the correct address. Okay, let me make some more space there. Okay, and so RSP plus what do we want? 520. So that should hit us. Yes, that is the return address 4018B7, and we want to go on FFD9B0. What have I written first of all? D9 40. What? Why have I written 40? It should be D9B0. Okay. Anyway, just a moment. D9B0. And we put this before again. And I'm going to like that. Is it okay? Python 3. Yes. Okay, it works. I just had the wrong address for some reason. I don't know how this happened. Sorry for the insanity. So now we can see that it has actually executed our code, and it prints a flag. And just for you to show you that our shellcode that we generated before is actually correct, I'm going to go here and I'm saying I'm not going to use shellcraft, which is the Pwn tools way, but I'm going to show you that we can also do it with our payload. So payload bytes, and then we're putting this the length of our payload. Length of payload bytes, and we should be good to go. Run that again. Oh no, it didn't print. Hey, 10 to 11 kilobytes plus. Why isn't my shellcode working, man? Anyway, I don't know why this shellcode is not working, but it works with the shellcraft actually. Something to think about. I don't know. I need to figure out why the raw shellcode bytes are not working, but it should be working with the shellcraft payload. And kinda, I would say that this kinda concludes this demo of running shellcode. I think I need to go sleep. But let's go back to here, and I'll leave you with something to play around after this. So this works. Okay, it prints flag he. Okay. They're reptilians, I know. Okay, I don't know why our shellcode is not working there. I need to figure it out. But here are some again what we talked about with Pwn tools, how to actually use Pwn tools. You can use P and U to actually pack and unpack, numbers. So like we did with the pointer, it has a context that you can say I'm doing this on MD64, I'm doing it on I36, I'm doing 386 or whatever. You can send line or send bytes or receive until or receive line, all that stuff. You can talk to a remote. So instead of going here and saying process, instead of going here and saying process, you can say remote, and it's going to connect to an IP and the port, and that's how all the CTF challenges are actually working right now. Okay, so yes, you can assemble stuff. You don't have just to say, shellcraft blah 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 .cat or shellcraft sh or whatever. You can assemble your own structures. You can say blah blah that and assemble it in there. So we could potentially take all our raw shellcode and assemble it in Pontools if we want. And we can, we can write the shellcode as the thing I told you now. And can also, it has like cat, exit, sh, it can do a reverse shell, can do many, many interesting things. So the task for you after this talk would be to actually run this buffer overflow proof of work thing, right? Okay, so I've made this bufo program now where you run it. It's going to, once you run it, it's going to ask you to calculate the sum of some numbers, right? So that forces you to use Python. It's proof of work, right? But you can read it. And then if you do this sh, if you see this bufo sh, it creates a flag for you. It puts it on actual /flag with sudo, and it runs this program with sudo, and it runs it on port 4921. So you just run this. And you would just run this. It would ask for your sudo password. It's fine, give it. There is nothing sketchy there. And it's running on the port 4921 of localhost. So your goal here would be to go automate this thingy with Pontools, so you can read a bunch of numbers and add them and pass them back to the program. Okay, so you kind of play around with Pontools and then kind of run the same bug. It's the same bug of the program, but you need to find the new addresses with GTP, right? And get the flag. I mean, you see the flag right here, but I mean, get it to print the flag for you. That will prove to you that you have understood what we did today. So that's the task that you have if you want to do it by yourselves. And let's finally make the third level where we're going to stop, because I'm crashing here. Sorry for that. It was giant. I'm sorry. This is the third level of the Inferno, where we meet Cerberus, like, the dog with the 3 heads that guards the entrance. And this is to, the Guardian is going to tell us also about the mitigations to all that stuff. Okay. So if you notice how I have compiled all these things slowly, you will notice I have put various options that say, don't make it a position-dependent executable. Make it with an executable stack. Don't put a stack protector on. These are different protections that modern operating systems have to prevent buffer overflows. So when there's the idea of the non-executable stack, where the operating system maps the stack as non-executable, and then when you try to put your shellcode there and run it, it crashes. Okay, so how do you defeat that, right? I mean, you defeat it by doing return-oriented programming, which means that you'd never put shellcode in there. You just manipulate the return addresses so that the program executes things that it already has in there, and you kind of take these little Lego pieces and put them together into doing something like your shellcode. Okay, so you run a bit of a little gadget over here that does something, and another gadget over here that does something, and these are all things that the program already has inside it. But you chain them in a way that the side effects of those cause your shellcode to run, actually. Okay, so that's return-oriented program. There is address space layer randomization. Right now, we have been seeing these addresses in GDB. We go and put them in there, right? But the operating system now can randomize things and put them into place that we don't know. How do you defeat that? not that hard. Like you can maybe get a leak. You can find, you can maybe fix a string that is not null terminated, and now it will print some more memory after as it prints that string, and then you see an address there, and from that address you can infer where everything is laid out on the stack. And then by also using return programming, you also can bypass this because you jump into places that the program already has, right? So you don't need to put something and you don't know where you put it because you don't know where, because the stack is randomized. There are other more advanced techniques that are called CFI, like control flow integrity. So now programs are like, you're only allowed to jump into the beginning of a function. You can't jump midway into a function, and that kind of defeats ROP. So there are certain landing pads in functions that a program can jump to. There are new attacks called function-oriented programming, where you, instead of running a little gadget, a little, 3 or 4 instructions, you run a whole function. And that function has side effects, and then you use these side effects to actually execute your shellcode. So like you just run functions one after the other, and somehow this, like uh, does the stuff you want, which is crazy. Now, there is the meme of writing everything in Rust. Unless the whole operating system and unless the whole architecture has this sort of guarantees, then these bugs are going to keep existing, because you might write whatever you want in Rust, but the moment you hit the kernel and hit C, there's no more Rust. Okay. And especially when you have a complex things like Rust and you interface with another complex thing like the Linux kernel, in that interface, you're going to have bugs. And I can argue that a lot of bugs, new bugs, are going to be generated by trying to connect Rust to C, like completely new bugs of, these systems having a confused API one with the other. Like, one will think this is a uint64, the other will think this is a uint32, and bam, you're going to have like an overflow there, for example. That's some, little reference you can use for some of the stuff. I'm going to add more into there. I think, yeah, that's about it. Stack canaries, good question. Stack canaries are still effective. So stack canaries are there. It's the fno stack protector that we add. They are effective, but there are, first of all, you can leak them sometimes. So as you leak a string, you can leak the stack canary and you can see the value of the stack canary. And also, there are problems when you have a forking server, as it's called, like, you have a, like, for example, HTTPD, for every new connection fires up a new, it forks and executes a new program. Or you have threads, right? We have POSIX threads. All these guys between them share the same stack canary. So that can be a problem, because you can use that to brute force the stack canary. So you put one byte, other byte, then you wait for the crash. At some point, you don't have a crash. So you found the first byte. You keep going like that, and you can brute force the stack canary like that, because it doesn't change on every, every time you connect. Every time you connect, it's just the same stack canary, so you can figure it out. Yeah, like yes, we. Nicholas says that we will still be using legacy code written C in the foreseeable future. So absolutely, yeah. And as long as the operating system is like that, in C, you won't escape. Another example I can give you from a recent CTF, they gave us like a program, a kernel written in Rust. Yet there were so many vulnerabilities in the kernel written in Rust, because even if the kernel is written in Rust, there were certain artifacts. I'll give you an example. There is a flag in modern CPUs called the DF, direction flag. If you set that flag to 1, then the string operations go the other way. Instead of going from lower address to higher address, it goes from higher address to lower address. So memcpy goes the other way. This is an artifact of the CPUs. Well, this kernel, for example, was not clearing this flag when it was going into system calls. So you could set this flag from the user land, make a system call, a memset, for example, or a memcopy, then it would go the other way, and you could override kernel instructions, for example, or kernel memory like that. It's crazy. Okay. And just because something is in Rust doesn't mean it's written correctly. Okay, it just doesn't have a class of bugs. And so yeah, I mean they're amazing things. They're like you again. I mean, the more complex you make something, I can argue that the more bugs you're introducing. So maybe a good way to actually not have bugs is make something very simple, done to the bare minimum, and then that can also be a way forward. I thought. Anyway, that concludes this giant talk. Thank you for persevering, um, and I hope you can play around a bit with these skills that we learned, and you can reach out. And when you get stuck, you see, like, I mean, there are mistakes and there are places that you get stuck. That's normal, right? That's the real life of debugging and doing that sort of thing. I don't think you can go 100% smoothly because it's complex and you will make mistakes. So don't worry about it. Empower yourself. Right?